Welcome to the course, Machine Learning with Hands-on Experience in Python and R, under Part 4, such as K-means clustering and hierarchical clustering. This course is fun and exciting, but at the same time, we dive deep into machine learning. It is structured the following 10 parts to be the master machine learning on Python and R. In this video of Part 4, we will discuss following two important parts of clustering.
Hello and welcome back to the course on machine learning. And in this section we're talking about the K-means clustering algorithm. And in this tutorial we're going to talk about the intuition behind K-means. So K-means is an algorithm that allows you to cluster your data, and as we'll see, it's a very convenient tool for discovering categories or groups in your dataset that you wouldn't have otherwise thought of yourself. And in this section, or in this specific tutorial, we'll learn how to understand K-means on an intuitive level, and we'll see an example of how it works. So let's dive straight into it. Let's make this topic, this complex topic, simple. Alright, so here we've got a scatter plot, and how does this scatter plot come to be? Well, let's imagine that we've got two variables in our data set, and we decided to plot those two variables on the x and y axis. So here we go, that's one variable, that's the other one, and this is how our observations are configured according to these two variables. So the question here is, can we identify certain groups among our variables, and how would we go about doing it? Can we maybe identify this is one group and this is the second group, or maybe this is one group, the second, maybe there's 4 groups or 5 groups, maybe there's 3 groups. How do we identify the number of groups? How do we identify the groups themselves? So what the K-means does for you is it takes out the complexity from this decision-making process and allows you to very easily identify those clusters. They're actually called clusters of data points in your dataset. So there we go. In this case, we have 3 clusters. And of course, this is a very simplified example. We only have 2 dimensions here, so 2 variables. K-means can work with a multi-dimensional object, so it can work with 3, 4, 5, 10 dimensions. This example is just for illustrational purposes so that we can visually see what's going on, but in reality they can be as many as 10, 100, any number of variables, and K-means will do that complex calculation for you. So it's an algorithm designed to find these clusters for you. And today we're going to find out a bit more on how the K-means algorithm works. So what is the step-by-step process? This is my favorite part. We're going to break it down to such a simple step-by-step process that it'll be extremely intuitive and simple to understand. Alright, so step 1 for the K-means algorithm is to choose the number of clusters K. And we'll talk more about how to select the optimal number of clusters further down in this section of the course. But for now, let's imagine that we've agreed on a number of clusters for a certain challenge. And let's say we've agreed that there's 3 clusters, or there's 5 clusters, or 2 clusters. And once you've done that, then you proceed to step 2. Which is to select at random K points, which will be the centroids of your clusters. And not necessarily these points have to be from your dataset. So as you saw, we had a scatter plot. You could select any points on that scatter plot. They don't have to be part of the observations that are plotted on the scatter plot. They can be any random X and Y values on your scatter plot, as long as you just select a certain number of centroids that are going to equate to the number of clusters that you have decided upon. Again, we'll see this in practice just now. Then you move on to step 3, where you assign each data point to the closest centroid. And that will form K clusters right away, immediately. So that's your starting clusters, and then there's going to be an iterative process to refine those clusters. And we'll see this in action, but basically, so you just check for every point in your dataset, which out of the centroids that you've identified in step 2, which of them is the closest to your specific data point. And then that's where that data point will be assigned to. And closest is a kind of a vague term here, because what kind of distance are you measuring it by? Is it Euclidean distance? Is it some other sort of distance? That can be better defined in your business challenge, but for the purposes of these tutorials, we're going to talk about Euclidean distances. And so that's basically geometrical distances in simple terms. Alright, step 4, where you proceed to after step 3, is to compute and place the new centroid of each cluster. And we'll see how that's done just now. So once you've found your clusters, you recalculate the centroids. Again, it's going to be much easier to understand this when we look at an example. Then in step 5, you reassign each data point to the new closest centroid. So basically you perform step 3 again, but we'll just call it step 5 here. And then if any reassignment took place, you repeat step 4. So it becomes an iterative process of step 4, step 5. And if no reassignment took place, you go to finish and your model is ready. I know this might seem a bit complex, but let's go through a visual example now so that we understand this on a very intuitive level. And then you can always reference this slide or this step-by-step rule further down when you're actually performing k-means clustering, or when you want to understand how it's happening and what's happening in the background of k-means clustering. So this slide will be a great reference point after we discuss this visual exercise that we're going to have just now. So let's move on. All right, so there is our scatter plot, and here we've got the observations in our dataset. They're plotted against 2 variables. And right away, the first question is, can you visually just quickly identify the final clusters that you think that we'll end up with? It's pretty tough, isn't it? And that is even when we just have 2 variables. Imagine how complex this situation or this challenge would be if we had 3 variables or 5 variables. We wouldn't even be able to plot a 5-dimensional scatter plot like that. So that's where k-means clustering comes into play, and that's where this algorithm will help us simplify the process. So let's see how it will perform in action. So in this case, we're actually going to manually perform the k-means clustering algorithm. So something that would normally be done by tools of your choice, such as R or Python or any other tool. But in this case, just so that we can get very comfortable with this algorithm, we're going to do it manually and see exactly how it works. All right, so let's go through the steps. Step 1, choose the number of clusters k. And let's say we somehow identified that the optimal number of clusters is equal to 2. Again, we'll discuss how to find the optimal number of clusters further down in the section, but for now, let's agree that for this challenge, it's just 2 clusters. All right, and then step 2. Select at random k points, which will be the centroids of your clusters, and not necessarily from your dataset. So what that means is that they can be actual points in your dataset, or they can just be random points on your scatter plot. It doesn't matter where you select them. So let's say we selected these 2 centroids, the blue centroid and the red centroid. Next step is step 3. Assign each data point to the closest centroid, and that will form k clusters. So basically, for every data point in our dataset, what we need to do is identify which of the 2 centroids, blue or red, is the closest. So let's say for this data point, obviously blue is closer than red, so it would be assigned to the blue cluster. For this data point, blue is again closer than red. For this data point, red is closer than blue. And so we could keep going like that for every data point and assign it to one of the 2 centroids. But we're going to use a quick hack here. We're going to use something that we learned from geometry. So what we're going to do is we're going to just connect these 2 centroids with a line like that, and then we'll find the center of the line, which is over here, and we'll put a perpendicular line exactly through that center like that. And so from geometry, we know from high school geometry, or maybe at university, or even if you didn't have geometry, it's a very straightforward concept that any point on this green line is equidistant from the blue and the red. So if I take this point, it will be the same distance to the blue centroid and to the red centroid. If I take this point, it'll be same distance to blue and the red. So this whole line is equidistant to the blue and the red, and that's how we constructed it. And so based on that, it now is obvious that any of our points on the scatter plot above the green line is closer to the blue, and any of the points below the green line is closer to the red. And that's how we're going to just color our points. It's a very quick way of coloring them. Again, you could totally go through every point and individually identify which one to which centroid is closest, but just for our sake, while we're doing this exercise, it's going to be faster if we apply this quick hack method. So there we go, we've colored our centroids, or our points on our scatter plot. Before we continue, I do want to mention something here, that closest is a very, even though it seems straightforward, it's quite an ambiguous term, because closest, when you're visualizing things on a scatter plot, yes, it's pretty straightforward that it's the distance, right? But at the same time, in mathematics and in data science, there's lots of different type of distances. Like the one we're using is Euclidean, and the question is, should you be using Euclidean distances, or should you be using some other type of distances defined for your challenge? And that is something up to you to decide, and there's something for you to specify for the algorithm what type of distance you're going to be using. But for our sake, we're just going to be using Euclidean distances for the illustration purposes. And basically, that's just a very straightforward, simple geometrical distances between two different points. So that's just a caveat there. And if you'd like to research more about distances and what other kind of distances you can use, just make sure to look into that, because for some challenges, sometimes you might want to use non-Euclidean distances that are defined in other specific ways. All right, so with that in mind, let's proceed to step 4. Step 4, compute and place the new centroid of each cluster. So basically, right now we've got the new points, all the blue ones excluding the centroid itself, and all the red ones excluding the centroid itself. And we need to find out where the actual centroid, the new centroid for the blue points is, and the new centroid for the red points is. And the way to think about it is, imagine that the centroids themselves, they are weightless, but these other points, they have a certain weight, say, let's say 1 kilo each. Then you need to find the center of mass, or the center of gravity of these centroids, and you need to pinpoint it on your scatter plot. So for the blue cluster, it'll be somewhere here. For the red cluster, it'll be somewhere over here. And the way to think about it on a 2-dimensional scatter plot, you kind of like can just visually see where it is, or you can just look at the x, let's say the y coordinates for all of the blue points, and find the center of gravity for the y coordinates, which will be somewhere here, and then do the same thing for the x coordinates, find the center of gravity, which, or like the average of the x coordinates, which will be over here. So that's how you get your new centroid for the red and blue clusters, and so we just move our centroids into them. Next, you perform step 5. So reassign each data point to the new closest centroid, and if any reassignment took place, then go back to step 4. Otherwise, you may finish your algorithm, meaning that it has converged. So let's do that. Let's see how now the data points will reassign to the new centroids. So if we put our line through the scatter plot, you'll see that there is 1 point, or no, there's actually 3 points. This point is closer to the blue than to the red, and these 2 points are actually closer to the red than to the blue. So now we will recolor them. There we go. So now we've got a new clustering, and some reassignment did take place, so we're going to proceed back to step 4. So we're going back to step 4, compute and place the new centroids for each cluster. Same thing, find the center of mass for this centroid, find the center of mass for this centroid, place the centroids in those locations, and now repeat step 5, reassign each data point to the new closest centroid. So we're going to put the line through the chart, so the equidistant line between the two centroids. As you can see, this point is actually now in the blue cluster rather than being in the red. Reassign that point, and what happens next is, again, we return to step 4. So if I go back here, you'll see that a reassignment did take place, so we're going back to step 4, and that's where our new clusters are going to be located, our new centroids. Move them there, repeat step 5. As you can see, it's an iterative process, which is going to keep going like this until the algorithm converges. So there's our equidistant line. As you can see, 1 point needs to be reassigned. It gets reassigned. So now we go back to step 4, compute and place the new centroids for each cluster, move our centroids, and now reassign each data point. So repeat step 5. And as you can see, this time the equidistant line does not make any points reassigned. So as you can see, all of the points are already in their correct clusters. And that means no reassignment took place during this step, so we can proceed to completing our algorithm. This means that the algorithm has converged. So there we go, those are our clusters and the model is ready. And so now we can just remove the centroids and the equidistant line, and there we go, that's our final result. So as you can see, that's how the k-means algorithm works. It's very, very intuitive and straightforward, just an iterative process. And if we compare it to what we had at the start, this is what we had. As you can see, it's not that obvious how the clusters would have been arranged. For instance, you might have thought that maybe this could be a cluster on its own, and this could be a cluster, or maybe this bottom part would be a cluster and this top part would be a cluster. But based on the k-means algorithm, what we got as a result is these two clusters. So the points in each cluster are not exactly very similar to each other, but this is what the k-means algorithm is suggesting. Hopefully you enjoyed this tutorial, and hopefully now we've demystified the k-means algorithm and we've broken it down into simple terms, and I look forward to seeing you in the next tutorial. Until then, enjoy machine learning. Hello and welcome back to the course on machine learning. Today we're going to talk about a specific aspect of the k-means algorithm, which is the random initialization trap. So let's have a look at this phenomenon and see what it's all about. So, random initialization trap. So here we've got a scatter plot, again with two variables, so we've got the x and y coordinates, and in this case, let's say we're going to choose 3 clusters. So right away you kind of tell which is the final result. What is the final result going to look like if we choose 3 clusters? It does look like you can pretty easily spot them here, but let's nevertheless form this operation, this algorithm, and if we initialize our centroids like this, then what we'll get is, because we already kind of can tell that probably that's a cluster, that's a cluster, and that's a cluster, so just to make the algorithm a bit faster so we don't have to do too many easy steps and iterations, we're going to select our centroids like this, and right away if we perform the algorithm we'll get these clusters. And next is, even if we move around the centroids, so we find the centroids of each of these clusters, nothing's going to change. So you can, in your own time, you can perform the steps that we learned about in the previous tutorial and see that nothing will indeed change because of the way we selected the centroids. This is already the final result. So those are going to be the clusters that we're going to end up with. So that's kind of the end result of the k-means algorithm, because we selected the clusters, the centroids, in the places where we did. Now, the question is, what if we select the centroids in different locations? Will we be able to change the result? Will the result be different? And of course, an algorithm has to be, what we want from this algorithm is for it to give us a deterministic result, because we can select the centroids at random, and therefore we don't want that selection of centroids to affect how the clustering is going to happen. But let's have a look and see what happens. So what will happen if we had a bad random initialization? So bad is like a term we're going to use loosely for now, but you will see why we're using bad random initialization just now. So again, we're going to go through these steps that we discussed in the previous tutorial. We're going to choose the number of clusters, which is 3. We'll select at random 3 points, which will be our centroids. We'll assign each data point to the closest centroid that will form k clusters. We'll compute and place the new centroid for each cluster, thinking in terms of center of mass or center of gravity. And step 5, we'll reassign each data point to the new closest centroid. If any reassignment took place, we'll return to step 4. Otherwise, we'll go to the end because the model has converged. So these are the steps we discussed previously. Let's have a look at them in action. Alright, so 3 clusters, and this time, instead of selecting the centroids here, here, and here, what we're going to do is we're going to select them differently. We're going to select the centroids like this. So we'll put 1 centroid here on this side, 1 centroid here, and 1 centroid here. So let's have a look what happens now. If we draw a line, so this time we have 3 clusters, 3 centroids, but the principle is kind of the same. We still have a point which is equidistant from all 3 of them. So this point over here is the same distance from all 3. And then this line is equidistant from these 2. This line is equidistant from these 2. This line is equidistant from these 2. Again, this is not part of the algorithm. As part of the algorithm, you would just take each individual point, you look at this point, and you would see which centroid is the closest. So this time is green, you'd color it green. This one you check again, you'd color it green. This one you check again, color it green, and so on. Then this one is the closest to red, you'd color it red, and so on. But just to make things easier for ourselves, we're going to use this little hack. We're going to use these lines to say anything in this part of the chart is going to be closest to red, just because these are equidistant lines. Anything in this part of the chart is going to be green, anything in this part of the chart is going to be blue. It'll just save us time. So based on this method, we can tell right away that this is the red cluster for now, this is the blue, this is the green. So now we've assigned each data point to the closest centroid. That's great. Now we're going to move on to step 4, and we're going to move these clusters. So we're going to recalculate, compute, and place the new centroids for each cluster. So there we can see that that is probably the center of mass for the red points. That's the one for blue points. That's the one for green points. So we move our centroids to the new locations. And now we're going to perform step 5. We're going to reassign each data point to the new closest centroid. So again, we're going to use that quick hack with the lines. Let's see how the lines will look like this time. There's our new equidistant point, and these are the equidistant lines. So this time you can see that nothing will change. The red points are already in the red corner, blue points are in the blue corner, and green points are in the green corner. So nothing is going to change. There will be no reassignment, so we don't go to step 4. We instead go to finalizing the algorithm because it has converged. So there we go. That is our model. It is ready. And as a result, we have these 3 clusters. Now, these 3 clusters are different to what we saw at the start. So let's have a look. This is what we saw at the start. We're going to call them the true 3 clusters because you can tell just from the chart, you can tell that these points would most likely form a cluster, these would form a cluster, and these would form a cluster. Just by looking at it, you can intuitively tell that is the case. This is what we got at the start of the tutorial, and this is what we got now. So you can see that the 3 clusters are different, and therefore what we have is a situation or a phenomenon where the selection of the centroids at the very start of the algorithm can potentially dictate the outcome of the algorithm. And that's not a good thing because the centroids are selected at random. So how do you combat this? How do you battle this? Well, the answer is actually not as straightforward. There is a addition or a modification to the k-means algorithm that allows you to correctly select the centroids. And the solution here is the k-means plus algorithm. Now, at the same time, I wanted to mention that we're not actually going to delve deeply into the k-means plus algorithm and how it's structured. You can definitely read up more about it on Wikipedia or other sources. It is quite a involved approach in how that selection occurs. But the good news is that all of this happens in the background. So the k-means plus happens either in R or Python or whatever tool you're using. You don't need to actually implement it. So it's just a good idea to be aware of this issue, that there's a true cluster result that you're after, and there can be some false or some non-desirable clustering results or clustering outcomes of the k-mean clustering algorithm. It's good to be aware of that issue, and it's also good to know that the tools that you use will be, or make sure that the tools you're using are going to be implementing that specific selection of the random centroids at the very start so that you get the good result. So definitely, if you are more interested to learn more about the k-means plus algorithm, definitely read up about it. But otherwise, it's not something that you really have to worry about. It's just something that you need to keep in mind and make sure or be confident that the tools you're using are bypassing this initialization trap. So hopefully you enjoyed today's tutorial, and I look forward to seeing you next time. Until then, enjoy machine learning. Hello and welcome back to the course on machine learning. In the previous tutorials, we learned quite a lot about the k-means algorithm. We talked about how it works in the background. We actually performed a manual k-means algorithm, which was lots of fun. Then we talked about the random initialization trap and what the k-means plus is. And in all those scenarios, we kind of worked with a predetermined number of clusters, whether it was 2 clusters or 3 clusters. And we talked about somehow finding out the correct number of clusters for a given data science problem. In today's tutorial, we're actually going to talk about the algorithm behind finding out the right number of clusters. So we'll learn how to decide what number of clusters to input into your k-means algorithm. So let's get straight into it. Here we've got a challenge or a data science problem. Again, we've got only 2 variables, the x and y coordinates. Just for simplicity's sake, in reality it can be any number of columns or variables. And here we've got the scatter plot representing our data set. Now if we run the k-means clustering algorithm on this dataset with 3 clusters, or with k predetermined to be 3, then the result will look something like this. And not just something like this, but exactly like this. We've got the 3 clusters that have been identified, and we already know that we would need to run the k-means plus algorithm just to avoid the random initialization trap. But again, for simplicity's sake, we're just going to call it the k-means algorithm. So we've got the 3 clusters. Now, in order to understand if, for instance, 2 clusters would have been better in this scenario, or maybe 10 clusters would have been better, we need a certain metric. We need a way to understand or evaluate how a certain number of clusters performs compared to a different number of clusters, and preferably that metric should be quantifiable. So what kind of metric can we impose upon our clustering algorithm that will tell us something about the final result? And there is such a metric. It's called the within cluster sum of squares, that hence the WCSS on the left. And that is the formula, how it's calculated. This is an example for 3 clusters. Now, at first glance, this formula might look a bit overwhelming or complex, but in reality, it's super simple. So in line with our mission, making the complex simple, let's break it all down. What is going on here? Well, we've got the 3 elements and each sum, so this symbol stands for sum. Each sum is calculated for each cluster. In fact, it's calculated within that cluster, hence the W at the start. So let's look at one of them. Let's look at the central one, for instance. Here we're taking every point inside cluster 2, and that's exactly what is written out here. And this is, believe it or not, a valid way to write this sum. So you just write the P with the index I is inside cluster 2, and we're going to take a sum across those points. And what we're summing is the distance between each point inside cluster 2 and the centroid of cluster 2. And then we're squaring that distance. So we're taking the sum of those squared distances. So now if we have a look at our chart, I'm going to keep the WCSS on the left. So for instance, for cluster 2, there it is. We're taking the centroid and we're calculating the distance to every single point. So to that point, then we're squaring it. To that point, then we're squaring it. To that point, then we're squaring it. To that point, we're squaring it, and so on. So we're taking the square, the sum of all the squares of all these distances, and we're summing it. And then we're doing that. So we're doing that for the first cluster, we're doing that for the second cluster, and we're doing that for the third cluster as well. And so as a result, we get this total sum, so the full sum, and that is going to be our metric. And actually, it's quite a good metric in terms of understanding or comparing the goodness of fit between 2 different k-means clusterings. And how do we know that? Well, let's have a look. Let's rewind back to when we had one cluster. Let's see how that metric WCSS is going to change as we increase the number of clusters. Alright, so there is our chart with just the one cluster. As you can see, that is our centroid, and for every single point we have to measure the distance between that point and the centroid. Then we have to square that distance, and then we'll have to add all those distances up. As you can see, we'll get quite a large value because this centroid is quite moved away from all of the points. They all have to reach towards it. So let's just visually remember what this looks like, and that will help us kind of remember what that distance is, not in terms of the absolute value, but just what it feels like. It's quite a large distance right now. So I'm going to increase the number of clusters to 2, and let's see how everything changes. So there we go, that's 2 clusters, and as you can see, now instead of having one centroid in the middle, we have 2 centroids. So each one of these points no longer has to reach all the way to the middle, or the distance isn't that great. All you have to do is just calculate the distance to this centroid. As you can see, it's less. And then for these centroids, for all of them here as well, the distance to this centroid is less. They don't have to reach all the way to the middle when you're calculating that distance. So there we go. That means that the total distance, or the total WCSS that we see here, is going to be less than when we had one centroid. Now, once again, we're going to increase the number of clusters, so this time to 3. So just remember visually what 2 clusters looks like, and then we'll compare to the next image. So there we go. Now we have 3 clusters, and as you can see, nothing changed in cluster 1. So this sum is going to be the same. These 2 sums have changed. So now instead of one cluster, these 2 groups of points are recognized as separate clusters, and therefore they have their own centroids, and the distance has again decreased because you can see now all of these points are closer to their own centroid than they were to the centroid which was in the middle, and again these points are closer to this centroid overall than they were to the centroid here in the middle. So therefore, as you can see, the WCSS distance is decreasing. And what is the limit of that? How far will it keep decreasing? Well, let's think about it. Let's say we increase the number of clusters to 4, 5, 6, and so on. How many clusters maximum can we have? Well, we can have as many clusters as there are points elements in our data set. So as many points as we see on our chart, that's how many clusters we can have. So if we have 50 points, we can have up to 50 clusters, because after you go over 50, or after you go over the number of points, there's no more points to actually cluster. Every single point has its own cluster. So, and in that case, what will the WCSS equate to? I'll give you a second. If you want to, you can pause this video just to think about that for a second. If we've reached the number of clusters equivalent to the number of points in our chart, or the number of which is the same thing as the number of elements in our data set, then what does WCSS equate to? And exactly right, the WCSS will equate to 0, because every single point has its own cluster, and therefore it has its own centroid, and that centroid is going to be exactly where that point is, and therefore the distance between the point and the centroid is going to be 0. If you square that, it's going to be 0, and if you add up all those squares, it's still going to be 0. So as we can see, the WCSS will decrease from a substantial value when we have one cluster all the way down to 0 as we increase the number of clusters. So it is a good metric, but at the same time, it's constantly decreasing, right? So it's constantly getting better and better and better. And that's because, as you can see, the less the WCSS, or the higher the number of clusters, the better the goodness of fit. We're fitting our data better and better and better, and therefore the lesser the WCSS, the better the goodness of fit is deemed to be. But how do we find the optimal goodness of fit? Yes, it keeps getting better, but is there a sacrifice that comes with that improvement? And that is exactly the case. Let's have a look at this visual chart. This chart represents how the WCSS changes as we increase the number of clusters. And as you can see at the start, the WCSS starts at quite a large number. It doesn't really matter what this number is measured in, what the absolute value is, and things like that. What matters is how it changes. So the relative comparison between different k-means clustering methods with the different number of clusters. So you can see here that it jumped from 8,000 down to 3,000. That's a massive change of 5,000. Let's just call them units, 5,000 units. And then from 3,000, as we increase the number of clusters from 2 to 3, it jumped from 3,000 to 1,000. Again, quite a large drop. And then from 3 to 4, what's going to happen is going to jump from 1,000 to maybe 800, then from 800 to 600, 600 to 500, and so on. So as you can see, the first two improvements, or first two changes from one cluster to 2, from 2 to 3, created some huge jumps or huge drops in the WCSS. Going forward, the WCSS drops not as substantially. And this is our hint at selecting the optimal number of clusters. And the method we're going to use is the elbow method, and it is actually very visual. All you have to do is look at your chart and look for that change, or that kind of, like, it does look like an elbow. Look for that elbow in your chart where the drop goes from being quite substantial to being not as substantial, the improvement is not as great. And therefore that point in your chart is going to be the optimal number of clusters. In this case, it is indeed 3 clusters that is the optimal number. And as you can imagine, this method is quite arbitrary. So sometimes the situations are not as obvious. Sometimes the elbow might not be as evident as in this case, and therefore somebody might pick one number of clusters, someone else might come along and pick another number of clusters. But that is a judgment call that you need to make as a data scientist. Sometimes you need to decide on how your analysis is going to be structured, and this is one of those cases, because you are deciding what type of k-means clustering algorithm to run. You're inputting that value of k, and yes, it can be arbitrary, but if you're not really sure, then you just need to kind of run the k-means, for instance, with 3, look at it with 4, look at it with 2, and like see what the difference is, and make that judgment call on which k you think is optimal for your analysis. Because ultimately you are the person creating this analysis, and you need to decide which number of clusters is optimal. So the elbow method is just an approach that can help you make that decision, but at the end of the day, it is your decision. So there we go. Hopefully you enjoyed this tutorial, and now your arsenal of k-means clustering is quite broad. You have quite a few tools in there, and I can't wait for you to jump into the practical application of this method. Adeline has prepared some very interesting code challenges for you, and you'll be working with this method both in R and Python. It's going to be very exciting. So good luck with that. I'll see you next time, and until then, enjoy machine learning. Hello and welcome back to the course on machine learning. This is a quick tutorial to update you on how to download the dataset for this section. If you've seen this tutorial before, then feel free to skip it. However, if you're jumping into this course, into this section directly, just because you perhaps needed to learn this specific machine learning algorithm, then make sure to go back and first complete the data pre-processing section, because you will need that throughout this section as well. And you'll also need the machine learning template folder, which we're going to use just now. So in order to get the dataset for this section, you need to go to www.superdatascience.com/machine learning. Machine learning is spelled with a hyphen in between, 2 words with a hyphen. And then you'll see this whole page dedicated specifically to this course, and all the datasets for this course are available on this page. And so let's say that today you want to do the k nearest neighbor algorithm section. Of course, it is most likely a different section. I'm just going to use this one as an example, but just go ahead and find your section on this page and then perform the same exact steps, and you will see how to download and install the dataset. So I'm going to do it for the k nearest neighbors algorithm section. So just go ahead and click and download that dataset. It should download pretty quickly, unless it's one of those larger datasets that we also have in this course. Then you have the dataset here, and we already have the machine learning A to Z folder, which we created or downloaded from the data pre-processing section. So now we're going to take this, we're going to open the folder. We're going to go to into the part which this algorithm relates to. Then we'll find the algorithm, there it is, k nearest neighbors, and then we'll take this folder, this dataset folder, and we'll drag it in here. Now we're going to unarchive this folder. So I'm going to say right click, extract here. If you get this Mac OS folder, sometimes it appears, then you don't really need it. Everything is in the normal folder, so you can get rid of the Mac OS folder, and you can get rid of the zip folder now. And also with the k nearest neighbors, you just need to take all of the files and copy them into this folder here. So we don't need this another level of hierarchy, so you can now delete it. So basically what you should be left with is machine learning A to Z, then the part that the algorithm is in, then the section that you are interested in, and then this is where all the files should be stored. So here you'll have some Python and R templates, and you'll also have the dataset. That's the one that you will need in this section of the course. So there we go. It's a very straightforward process, and the beauty of it is if you use our machine learning A to Z template folder, which we provide at the start of the course, you will end up with a very structured set of folders which contain your datasets, and you will build them up as you go through the course, and therefore you'll have the whole library, and it will be nicely and neatly organized. I hope you enjoyed today's session and have fun on the practical tutorials, and I'll see you here next time. Until then, enjoy machine learning.
Hello and welcome to this Python tutorial. So in the previous section we introduced our business problem, and today we are going to solve it using k-means in Python. So here we are in Python. First thing that we have to do is set our working directory. So we click on this folder here, then we go to our machine learning folder, then part 3 clustering, and eventually we open our k-means clustering section folder and we click on choose. Perfect, that found our folder that contains the dataset, and let's not forget to click here to set our folder as working directory. And now let's implement our k-means algorithm step by step. So first step as usual is to import the libraries. So we write the comment importing the libraries, and just below we import the 3 essential libraries: NumPy to use mathematics, matplotlib to plot nice charts, and pandas to import and manage datasets more easily. We select our 3 imports and we press Command and Control plus Enter to execute them. Perfect. Now let's move on to the second step, which is to import the mol dataset with pandas. Okay, so here I'm gonna write this comment to introduce this new step, importing the mol dataset with pandas. And to import this dataset, we simply write dataset equals pd.read_csv, and in parentheses we put the name of our dataset in quotes, mol.csv. make sure that this dataset is in your working directory folder, and if that's the case, let's select this line of code and execute. Great, now let's go to Variable Explorer to see what our dataset looks like. Here it is, let's double click on it, and that opens the mall dataset. Okay, so let's re-explain what this mall dataset is about and what our mission is. There is a big mall in a specific city that contains information of its clients, the clients that subscribe to the membership card. When the clients subscribe to the card, they provided their information like their gender, their age, and their annual income. And because they have this card, they use it to buy all sorts of things in the mall, and therefore the mall has the purchase history of each of its client member, and that's how they obtain the last column here, which is the spending score. So as a reminder, the spending score is a score that the mall computed for each of their clients based on several criteria, including, for example, their income, the number of times per week they show up in the mall, and of course the amount of dollars they spent in a year. And based on all this, they computed this metric that takes values between 1 and 100, so that the closer the spending score is to 1 and the less the client spends, and the closer the spending score is to 100, the more the client spends. And eventually, after collecting this dataset, the mall company hired you as a machine learning scientist to segment their clients into different groups based on these two metrics, the annual income and the spending score. And since the mall has no idea of what these client segments might be, or even has no idea about how many segments there would be, this is typically a clustering problem because we don't know the answers. So now let's start our mission and use the k-means algorithm to find out what those clusters of clients might be. So here we just imported the dataset. This dataset has been imported by Panda as a data frame, and now we are going to build an array containing the two columns we are interested in, the annual income and the spending score. And to do that, we simply write x, which is the name we give to our array, equals dataset.iloc, and in square brackets, a colon to specify that we want all the lines, comma, and now again in square brackets we're going to put the two indexes of our columns. So let's open again the dataset. Indexes in Python start at 0, so we count 0, 1, 2, and so annual income has index 3 and spending score has index 4. Okay, let's close that and let's get back to our code. We put here the two indexes 3 and 4 of our columns of interest, and eventually we end this line of code by .values. Okay, let's select this line of code and execute it. Perfect. It created the array X of our two columns, which we can visualize here by double-clicking on X. So now we are done with importing our data, and we are ready to move on to the next step. And that's when things start to get interesting, because right now we are going to start using k-means specifically. Okay, so since we have no idea what to look for, we actually don't know the number of clusters of clients to look for. And remember when we got our k-means intuition in the previous section, we saw that when we use k-means, we have to choose this number of clusters. And that's exactly what we are going to do right now. We are going to find out the optimal number of clusters for our problem. And to do this, of course, we're going to use the elbow method. So let's introduce this new step with the following comment, using the elbow method to find the optimal number of clusters. First, we import the k-means class from scikit-learn. So we write from sklearn.cluster import k-means. And now let's plot the elbow method graph. So to plot this graph, we are going to compute the within cluster sum of squares for 10 different numbers of clusters. So since we're going to have 10 iterations, we are going to write a for loop to create a list of the 10 different within cluster sum of squares for the 10 numbers of clusters. So we start by initializing this list that we call WCSS. WCSS equals empty square brackets, and then we start our loop. For I in range 1 to 11, so we choose 11 instead of 10 because the 11 bound is excluded and we want the 10 WCSS. However, the first bound 1 is included, so here I is going to take the values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now in each iteration of this loop, we are going to do two things. First, we will fit the k-means algorithm to our data X, and second, we will compute the within cluster sum of squares and append it to our WCSS list. Okay, so let's first fit k-means to our data X. We are going to create an object of the k-means class and call it k-means. So we write k-means, that's the object, equals k-means with capital K and M, that's the class, and within this class we're going to input several parameters. The first parameter is n clusters, the number of clusters. And because we are testing several number of clusters to build our elbow method graph, the number of clusters and clusters here is going to be our variable I that is going to take the values from 1 to 10. Next parameter is init, the random initialization method. You can choose random if you want a complete random choice of your initial centroids, but we don't want to fall into the random initialization trap, so we're going to choose this very powerful method that we saw in the k-means intuition sections, which is of course the k-means plus plus initialization method. And therefore here we write init equals k-means plus plus between quotes. Then the next parameter is max iter. This is the maximum number of iterations there can be to find the final clusters when the k-means algorithm is running. The default value for this parameter is 300, and that's the value we are going to choose. Then the next parameter is ninit, which is the number of times the k-means algorithm will be run with different initial centroids. The default value for this parameter is 10, and we will leave it to 10. Then there are other parameters that we can add, like the tolerance for convergence, but we won't go into the details of them because we're going to leave them to their default values. Indeed, by not adding them into these parentheses, they keep their default values. However, let's add here the random state parameter, which fixes all the random factors of the k-means process, so that when we set it together to the seed 0, we will all get the same results. But you're welcome to try another seed or even remove this random state parameter to see what happens. Okay, so now we prepared the k-means algorithm, but we still need to fit it to our data X. And to do this, it's very simple. We just write k-means, which is the object that we just created, dot, then fit, and in parentheses, X. So fit is a method of the class k-means that of course fits the k-means algorithm to your data. And now let's do the second thing, which is to compute the within cluster sum of squares and append it to our list WCSS. There is actually another name for within cluster sum of squares, and that's called inertia. And thanks to the awesome scikit-learn libraries, there is actually an inertia attribute that computes the within cluster sum of squares. So to compute the within cluster sum of squares, we write the code k-means.inertia with an underscore, and to append it to our WCSS list, we write the code wcss.append, and in parentheses we put the inertia computation k-means.inertia. Okay, so we are done with our loop, and now we are going to plot the elbow method graph. So we write plt.plot, and then in parentheses, first we input the x-axis values, which are range 1 to 11 because we wanted 10 numbers of clusters, then comma, and then we put the values of our y-axis, which are of course WCSS. Then let's add a title to our chart by typing plt.title, and in parentheses we input the title, the elbow method. Then let's add a name to our x-axis by typing plt.xlabel and in parentheses number of clusters. And same, let's add a name to our y-label by typing plt.ylabel WCSS. And last but not least, to display the chart, we type plt.show parentheses. Alright, now I'm very excited to select this code section here and execute it to find out if there is an optimal number of clusters. So let's do that. Let's select our code here, Command or Control plus Enter to execute, and wonderful! We obtain a beautiful elbow method chart with a very obvious optimal number of clusters, which turns out to be 5 clusters. Indeed, we can see that the elbow is here, and when we project this point on the x-axis, we obtain x equals 5. Perfect! So now that we have the right number of clusters, we are ready to move on to the next step. And the next step is to apply the k-means algorithm on our data X, but this time with the right number of clusters. So let's introduce a new code section with the comment applying k-means to the mul dataset, and let's immediately fit the k-means algorithm to our data X with the right number of clusters, 5 clusters. So we already know how to do that since this is exactly what we did in the loop, and accordingly we write k-means, the object, equals k-means, the class, and in parentheses we input number of clusters and clusters equals 5. Then for the random initialization method we put init equals k-means plus plus, and then maximum of iterations 300, and init equals 10, and random state equals 0. So that's how we prepare k-means, and now we have to fit it to the data X. Only this time we're not going to use the fit method, but we are going to use the fit predict method that returns for each observation which cluster it belongs to. So that means that for every single client of our dataset, the fitPredict method is going to tell us the cluster to which the client belongs. And it will return these cluster numbers into a single vector that we're going to call ykmeans. And therefore here we write ykmeans equals kmeans.fitPredictX. Okay, perfect. Now let's select this code section and press Command or Control Enter to execute. Done. And now if we go to Variable Explorer, we can see that we have our new vector of cluster numbers, ykmeans, right here. So let's double click on it to open it, and let's also open the dataset. And now we can see that customer number 1 belongs to cluster number 4, customer number 2 belongs to cluster number 3, customer number 3 belongs to cluster number 4, and so on. Okay, so let's close that and move on to the next step. This next step is actually the final step, and this is where we get all the fun. Because we've done our job, fitting the k-means algorithm to our dataset, and now we look forward to seeing the results. And we are going to make sure to plot a beautiful chart with our 5 clusters well represented. Okay, so let's introduce this new step with the comment visualizing the clusters, and let's begin to plot the results. So basically we're going to make a scatter plot of all our observations, on which we're going to add the centroids and of course the clusters that we will make sure to highlight properly. So we write plt.scatter, and let's start by plotting all the observations belonging to cluster 1. Before we move on, let's just notice that in this ykmeans vector, the cluster numbers are not from 1 to 5, but from 0 to 4. So that means that our first cluster, cluster 1, corresponds to ykmeans equals 0. So in plt.scatter, we first take our dataset X, then in square brackets, we specify that we want the observation that belongs to cluster 1 by writing ykmeans equals 0, and then comma, and then we specify that we want the first column of our data X, so we type 0 because indexes in Python start at 0. And by doing that, we gave the X coordinate of all the observation points that belong to cluster 1. And now we have to do the same for the Y coordinate. So here we type comma, and then X, and in square brackets, ykmeans equals 0, and then 1 that corresponds to the second column of our data X, that is the Y coordinate. Good, and then we choose a size for our data points. Since we don't have too many observations, a good choice of size here is 100. Then we pick a color for our cluster. Let's pick red, and then we give a label to our cluster that we are going to call cluster 1 for now. And now let's copy paste this line of code 4 times to do the same for the other clusters. So here we put 1 for the second cluster, then 2 for the third cluster, then 3 for the fourth cluster, and finally 4 for the 5th cluster. Okay, and let's of course change the colors. Let's choose blue for the second cluster, green for the third cluster, cyan for the fourth cluster, and magenta for the 5th cluster. And of course, eventually we change the cluster labels: cluster 2, cluster 3, cluster 4, and cluster 5. Okay, and now let's plot the centroids. So it's the same as for the observation points, only this time we're going to use the cluster centers attribute that returns here the coordinates of the centroids. And to highlight them well, we're going to choose a bigger size, s equals 300, and the star color yellow. And of course we change the label to centroids. Then we add a title to our plot by typing plt.title clusters of clients. Then let's specify the name of the x-axis by typing plt.xlabel annual income $K, and the name of the y-axis by typing plt.ylabel spending score 100. Then since we specified all the different labels, we want to add a legend, so we type plt.legend. And last but not least, we want to display the chart, so we type plt.show. And now, moment of truth, let's find out what our 5 clusters look like. We select this code section here, and let's press Command or Control plus Enter to execute. Voila, our 5 final clusters. So let's look at them one by one. Cluster 1. Clients in cluster 1 have high income and low spending score. So in this cluster, clients earn a high income but don't spend much money. So we could call this cluster of clients Careful, for careful clients. Cluster 2. Clients in cluster 2 have average income and average spending score. So let's call this cluster of clients Standard. Cluster 3. High income and high spending score. So that is the cluster of clients that would be the main potential target of the mall marketing campaigns, and so it would be very insightful for the mall to understand what kind of products are bought by the clients in this cluster. So eventually we can give to this cluster the following name: Target. Cluster 4. low income but high spending score. So clients in this cluster earn a low income but don't care and spend much. So let's call this cluster of clients careless. And eventually cluster 5, low income and low spending score. So as opposed to the careless clients who have low income and spend much, we are going to call them the sensible clients. So now let's reselect and execute this code section with the correct cluster labels, and we get our final chart of the clusters of clients. Alright, we are done with the k-means algorithm in Python. Look at our code, it's structured, simple, and it does the job perfectly well. And you can use this code anytime you want for your work. You just have to replace the name of the dataset, change the indexes of the columns of interest, and then you just have to execute this code to find some answers of your business problem. And if you are doing clustering in more than 2 dimensions, then don't execute the last code section to visualize the clusters, because it's only for 2-dimensional clustering. However, later in this course, we will learn a technique that allows us to reduce the dimensions of our dataset. So if you reduce your dataset to 2 dimensions, then you can use this last code section to plot the clusters. And now to finish this tutorial, let's clear everything and reset by executing this line of code here without the comment. Let's also go here and press Ctrl L to clear the console. We select the whole code, execute it, and we make sure everything works fine. Thank you for watching this video, and I look forward to seeing you in the next tutorial. Hello and welcome to this R tutorial. In this tutorial, we are going to solve our business problem using the k-means algorithm in R. So let's start by setting a working directory. So we go to Session, Set Working Directory, and we click on Choose Directory. Then we pick our folder Machine Learning AZ, Part 3 Clustering, Section K-means Clustering, and we click on Open. Okay, now the first step is to import the mul dataset. So let's introduce a new code section with the comment importing the mul dataset, and we import our dataset by typing dataset, left arrow, read.csv, and in parentheses, mul.csv. Okay, let's select this line and hit Ctrl Command plus Enter to execute, and our dataset is now imported. Let's click on it to see it. Okay, so let's re-explain what this mul dataset is about and what our mission is. There is a big mall in a specific city that contains informations of its clients, the clients that subscribe to the membership card. When the clients subscribe to the card, they provided their information like their gender, their age, and their annual income. And because they have this card, they use it to buy all sorts of things in the mall, and therefore the mall has the purchase history of each of its client member, and that's how they obtain the last column here, which is a spending score. So as a reminder, the spending score is a score that the mall computed for each of their clients based on several criteria, including for example their income, the number of times per week they show up in the mall, and of course the amount of dollars they spent in a year. And based on all this, they computed this metric that takes values between 1 and 100, so that the closer the spending score is to 1 and the less the client spends, and the closer the spending score is to 100, the more the client spends. And eventually, after collecting this dataset, the mall company hired you as a machine learning scientist to segment their clients into different groups based on these 2 metrics, the annual income and the spending score. And since the mall has no idea of what these client segments might be, or even has no idea about how many segments there would be, this is typically a clustering problem because we don't know the answers. So now let's start our mission and use the k-means algorithm to find out what those clusters of clients might be. So here we just imported the dataset, and now let's create a variable x that will only contain the 2 columns we are interested in, the annual income and the spending score. So here we write x, left arrow, dataset, and then in square brackets we're going to put the 2 indexes of our 2 columns of interest. That is, if we go to dataset, since indexes in R start at 1, the indexes of our 2 columns annual income and spending score are 4 and 5. So here in the square brackets we put 4, 5, which means that we go from 4 to 5. Okay, let's select this line of code and execute it. Perfect. It created the array X of our 2 columns, which we can visualize here by clicking on X. Alright, now we have all our data well imported and well prepared, and we are ready to move on to the next step. And that's when things start to get interesting. Indeed, right now we are going to start using k-means. So remember, when we use k-means, we have to specify the number of clusters. But the problem here is that we have no idea of how many clusters of clients we are looking for. So we could fit k-means several times on our dataset with different numbers of clusters to test different outcomes, However, there is a much faster way that allows us to find the optimal number of clusters to use with k-means for our problem. And we are of course going to use the elbow method. So let's introduce a new section with the comment using the elbow method to find the optimal number of clusters. And in this code section, we're going to make a for loop to plot our elbow method chart. So since there are random factors in k-means, we can obtain slightly different results by using k-means several times. So in order to all get the same results, we are going to set the same seed. And to do this, we type set.seed, and in parentheses we can pick whatever number we like. Let's pick 6. Then we are going to use a for loop to compute some different within cluster sum of squares for different numbers of clusters. And we are going to place the different within cluster sum of squares in a vector. So let's start by initializing this vector by typing WCSS, left arrow, vector, and empty parenthesis. So that just initialized an empty vector, and now we're going to use the for loop to populate it with the different within cluster sum of squares. So let's write for, and in parenthesis, I in 1 colon 10. So in for loops in R, the lower bound and the upper bound are included. So here that means that I is going to take the values from 1 to 10 included. And then at each iteration, we directly compute the within cluster sum of squares for each number I of clusters by writing sum, and in parenthesis, k-means xi to fit the k-means algorithm to our dataset x with I clusters. And by doing that, we actually created an object of the class k-means in R. And if we select k-means here, press F1, and then scroll down to value, we see that this class has an attribute called withins that computes the within cluster sum of squares. So let's of course use it and type k-means xi and then $, withins. Alright, now thanks to this loop, the WCSS vector is populated with the 10 different within cluster sum of squares for the 10 numbers of clusters 1 to 10. Perfect, so now all we have to do left is plot the graph. So we type plot, and in parentheses we first input the x values, that means 1 to 10, then the y values WCSS. Okay, then let's select plot and press F1. We can specify a type of plot, P to have only points, L to have only lines, and B for both. And we are going to choose both. So B. Then let's give a title to our plot by typing main equals paste and in parentheses clusters of clients. Then we can give a name to our X label, so let's input xlab equals number of clusters, and we give a name to our y-axis, ylab equals WCSS. Now let's select this code section here, and let's execute it to see if we have an optimal number of clusters. And yes, we do! We can clearly see that the point here is the elbow, and when we project this point on the x-axis, we obtain 5 clusters. So that means that the optimal number of clusters for our problem is 5 clusters. And thanks to this insightful information, we are ready to move on to the next step. Because the next step is actually to fit k-means to the MAL dataset with the right number of clusters, 5 clusters. So let's introduce this new step with the comment applying k-means to the MAL dataset. Then let's set a seed so that we all obtain the same results. We can pick any number, let's pick 29, and then let's fit k-means to our data x. So we create the object k-means from the class k-means, and then let's select k-means here and press F1. The first argument we have to input is our data x, then the second argument is the number of clusters, and now we know it's 5. And then like in Python we can specify a maximum of iterations. Let's use the same value, itermax equals 300, and we can also specify the number of initial random sets, and start equals 10. Alright, now we have everything we need and we are ready to select this code section and execute it to fit the k-means algorithm to our data x. Here we go, and perfect! Now let's move on to the next step and let's get all the fun. Indeed, this is the fun part because we did our job fitting the k-means algorithm to our data x, and now we look forward to seeing the results. So let's immediately introduce this new section, visualizing the clusters. We are going to plot our clusters using the cluster library. So first thing we do is to import the cluster library, and to do this you can either go to packages and select cluster here, or we can type here library and then parenthesis cluster, which is a better way if you want to execute later the whole script. And now let's plot our clusters. To do this, we will use clustplot. Let's select clustplot here and press F1 to see the parameters to input. So the first parameter is our data x. For the second parameter, we input the vector of clusters, that is, the vector that returns for each observation which cluster it belongs to. And we can take this vector by typing k-means $cluster. then a parameter that we have to specify is lines. Because when you don't give a value to lines, some distance lines between the clusters will appear on your plot. And we don't really want that, so we're going to choose the value 0 so that no distance lines will appear on our plot. Then let's set the parameter shade to true, so that the clusters are shaded with respect to their density. Then same for color, let's set it to true. Then we have the parameter labels, and we're going to pick labels equals 2 so that we have all points and clusters labeled in the plot. Then we don't really want different symbols for the points in different clusters, so we set plot card to false. Then we have this cool parameter span that allows us to plot ellipses around the clusters, and in order to plot the ellipses, we will set it to true. And finally, we would like to add a title to our plot, so we write main equals spaced clusters of clients. Then we want to give a name to our x-axis, so we add xlab equals annual income. And same for the y-axis, ylab equals spending score. And now, moment of truth, let's find out what our 5 clusters look like. We select this code section here, and let's press Command or Control plus Enter to execute. Voila, our 5 final clusters. So let's look at them one by one. Cluster 1. Clients in Cluster 1 have high income and low spending score. So in this cluster, clients earn a high income but don't spend much money. So we could call this cluster of clients Careful, for careful clients. Cluster 2. Clients in Cluster 2 have average income and average spending score. So let's call this cluster of clients Standard. Cluster 3. High income and high spending score. So that is the cluster of clients that would be the main potential target of the mall marketing campaigns, and so it would be very insightful for the mall to understand what kind of products are bought by the clients in this cluster. So eventually we can give to this cluster the following name, Target. Cluster 4. Low income and low spending score. So as opposed to the careless clients who have low income and spend much, we are going to call them the sensible clients. And eventually cluster 5, low income but high spending score. So clients in this cluster earn a low income but don't care and spend much. So let's call this cluster of clients Careless. Alright, we are done with the k-means algorithm in R. Look at our code, it's structured, simple, and it does the job perfectly well. And you can use this code anytime you want for your work, you just have to replace the name of the dataset, change the indexes of the columns of interest, and then you just have to execute this code to find some answers of your business problem. And if you are doing clustering in more than 2 dimensions, then don't execute the last code section to visualize the clusters, because it's only for 2-dimensional clustering. However, later in this course, we will learn a technique that allows us to reduce the dimensions of our dataset. So if you reduce your dataset to 2 dimensions, then you can use this last code section to plot the clusters. And now to finish this tutorial, let's clear everything. So we click on this button here. Let's also go here and press Ctrl L to clear the console. We select the whole code, execute it, and we make sure everything works fine. Thank you for watching this video, and I look forward to seeing you in the next tutorial.
Hello and welcome back to the course on machine learning. And in this section, we're kicking off the tutorials for hierarchical clustering. Alright, so another very interesting topic ahead of us, and as always, let's make the complex simple and demystify what it's all about. Alright, so what is hierarchical clustering? Well, believe it or not, but if you have points on your scatter plot or data points like we looked at previously, this is a 2-dimensional space. If you apply hierarchical clustering, or let's just say HC for short, what will happen is you will get clusters, again, very similar to k-means. In fact, sometimes often the result can be exactly the same as k-means clustering. But the whole process is a bit different. So let's talk about it in a bit more detail. So the first thing that we need to note is that there's 2 types of hierarchical clustering: agglomerative and divisive. So agglomerative is the bottom-up approach, and you'll see in more detail just now what that means. So we'll be starting at the very bottom and then building our way up. Divisive is the opposite, starting at the top and dividing the clusters into multiple. In this course, we'll be focusing on the agglomerative approach. The divisive, we'll mention it a bit just now when we're talking about the agglomerative, but it's basically the same thing, but the other way around. It's the reverse of the agglomerative. And if you like, you can definitely research more about the divisive approach. But for now, we're going to focus on the agglomerative one. Alright, so the agglomerative hierarchical clustering. How does it work? Well, to start off, we're going to break it down into a step-by-step approach, and then we'll look at an example and manually perform the clustering. Alright, so step 1 in HC is to make each data point a single point cluster. So that forms n clusters. So if you have n data points, your first step is to look at each one of them as an individual cluster. Then step 2 is to take the two closest data points and make them one cluster. So to combine them into one cluster, and that forms n-1 clusters. Then step 3 is to take the two closest clusters out of the ones now that you now have and make them one cluster. That forms n-2 clusters. Then step 4 is to repeat step 3 until there is only one cluster. So basically you just keep repeating step 3 and combining points into bigger and bigger clusters until there's only one huge cluster left. So you just keep repeating step 3, and at the end you're done. So at the end you'll have one huge cluster left. And how to get from 1 to 2 or 3 clusters, how to get the final result that you actually want, we'll talk about that in this section as well. So that's the goal, of course. But one thing that stands out here is the words closest clusters. Now, we've already talked about distances, and we mentioned Euclidean, that you can use Euclidean distances or other distances, and that's totally fine when you're working with individual points. But here we're actually going a step even further, and we're talking about not just the proximity of points, but actually proximity of clusters. And this is something worth noting. So I'd like to pause here for a bit or like kind of step to the side and talk about the closeness of clusters and how you measure distance between clusters, because that can really affect your algorithm if you're using hierarchical clustering. So let's talk about that for a few minutes. So first of all, Euclidean distance, just to get this out of the way once and for all, Euclidean distance is in a two-dimensional space. It's calculated like that. So the distance, if you got 2 points, P1 with the coordinates x1 and y1, P2 with coordinates x2 and y2, then Euclidean distance, or the length of this line, is calculated as x2 minus x1, so that the distance between the x's squared plus the distance between the y's squared. So basically, and then you add them up and then you take the square root. So basically it's you've got a right angle triangle over here, and you've got the catet here, and you got another one catet here. I hope I'm pronouncing this right. And then this is the hypotenuse, right? So that is how you calculate the distance between the 2 points. So it's basic geometry back from high school, and there you go. That's just how Euclidean distance is calculated, and that's what we're going to be working with. But again, there are other types of distances that you could be invoking in your algorithms, and it really depends on the scenario and how your algorithm is going to be structured. But in our examples, we're going to be working with Euclidean distances because they're the more natural type of distance. And now let's talk about the distance between two clusters. So let's say you have two clusters, the red and the blue. How do you measure the distance between them? What is the definition of the distance between two clusters? It's not as obvious as it might sound at the start, because there can be a couple of options. For instance, you can option 1 is just take the two closest points and measure that and call that the distance between the two clusters. Option 2 is actually take the two furthest points and call that the distance between two clusters. That's also a valid approach. Option 3, take the average. So take the average of all the distances between the different points in the cluster, so all the combinations of different points, and take the average of that distance. Option 4 is take the distance between the centroids. So find the centroids and find the distance between the centroids and call that the distance between the two clusters. So it's a very important part of hierarchical clustering, what you define as the distance between two clusters, because that can significantly impact the output of your algorithm. Now, we're not going to delve much deeper into this. It's just something to remember, to note, and based on your particular situation, whether it's a business problem or other type of data science problem, based on what exactly you think is the best approach, you're going to need to define that in your algorithm. So just keep that in mind, that for the hierarchical clustering algorithm, the distance between clusters is a crucial element, and you need to remember what exactly you're setting it to be, how you're defining it in your approach. All right, so we've talked about that. Now let's move back to our example. So we've already looked at the step-by-step rules, and I'm a big fan of a step-by-step approach. Now we have that step-by-step approach, and it might have seemed a bit overwhelming as always because we didn't have an example, but now we're going to have that example and we're going to look at how to build those hierarchical clusters. So step 1, make each data point a single point cluster. That forms 6 clusters. Let's have a look at that. You can see every single point is a separate cluster. Next, take the 2 closest data points and make them one cluster. We can see that these 2 points are the closest, so we're putting them together in one cluster. Now we have 5 clusters, 1, 2, 3, 4, and these 2 are one cluster. All right, step 3, take the 2 closest clusters out of the ones we had and turn them into one cluster. So out of the clusters we had, because remember each point out of these 4, so if I go back here, each point here is a separate cluster and this is a cluster. So now just measure the distances between clusters. And let's say in our example, we're going to be talking about the distance between clusters as the minimum distance. So that would be the distance between those 2 clusters, that would be the distance, that would be, and so on. So you measure all the distances between clusters and you find out that these 2 are actually the closest clusters, and you combine them into one cluster. Next, you repeat step 3. So next, out of these clusters, out of 1, 2, 3, 4 clusters, so you can see we had 5, now we have 4. Every time you're reducing the number of clusters by 1. Out of these 4 clusters, which are the closest? Well, this seems as the closest cluster, so we're going to combine that. Now, out of these 3 clusters, which are the closest? Well, it looks like these 2 are, so you're combining them. And now we've only got 2 clusters left, so the last step would be to combine them because they are by default going to be the closest. So there we go, and so that is the end of our algorithm. That's how it converges. We've gone through the process of going from all points seen as an individual cluster, so each point is an individual cluster, to now we only have one cluster that combines all of the points. And so what's the purpose of all of this? What's the purpose of this exercise? The way the hierarchical clustering algorithm works is that it maintains a memory of how we went through this process, and that memory is stored in a dendrogram, and that's exactly what we're going to talk in the next tutorial. And once we've covered the dendrograms, it will make total sense why the hierarchical clustering algorithm does what it does and how it works. So hopefully you enjoyed today's tutorial. Can't wait to see you on the next one. Until then, enjoy machine learning. Hello and welcome back to the course on machine learning. In the previous tutorial, we talked about the hierarchical clustering, the intuition behind it and how it works, but at the same time we didn't quite understand what the whole purpose of HC was and what the benefit of it was. Yes, we went from a huge amount of clusters where every single point or data element was considered a cluster, and then to one big cluster, but as a result now we have one huge cluster. What's the point of all of it? How do we get to the result we want, the actual clustering? So like in k-means, for instance, we would have 2 or 3 clusters. How do we get to that right number of clusters? So this is where the dendrograms come in, and they will help us understand everything. So let's get straight into it. So here I've got a chart on the left which contains 6 points. And on the right, I've got another chart. We're going to use this chart to create a dendrogram. Now, I know it might sound a bit confusing at first, especially because we haven't talked about dendrograms, but through creating one, we will learn what they are. So first off, just to make things a bit more legible, I'm going to add the points at the bottom so that they're a bit bigger so we can see them better. And so there they are, the points just listed on the bottom. On the vertical axis we've got Euclidean distances, and it'll all make sense just now. So we're going to now go through the HC algorithm and slowly create those clusters. So to start off with, every single point is an individual cluster, right? So every single one of these points is an individual cluster. Next, what we're going to do is we're going to find the 2 closest points, which are these 2, and put them into one cluster. So that's our step 2 in our algorithm. So there we go, that's the 2 closest points, and now we're putting them into one cluster. Now what we want to do on this diagram here, on the dendrogram, is we want to somehow signify that these were indeed the 2 closest points, because the dendrogram is kind of like the memory of the HC algorithm. It's going to remember every single step that we're performing. So there they are, those 2 points, P2 and P3. How do we signify that we've just connected them and that they were the closest? Well, to connect them, we would use like a horizontal line, but then where would we put it? Would we put it at the very bottom? Would we put it a bit higher? What's going to determine the distance, how high we're going to place this line? So this line is actually placed, this height actually has a meaning. This height is the Euclidean distance between them, and it also represents the computed dissimilarity between the 2 points or the 2 clusters. And what that means is the further away 2 points are, so for instance P2 is that far away from P3, and this could be a variable, for instance could be the age of a person, right? And this variable could be for instance the salary of a person, right? Or this variable could be how long a person has been with the company, and this variable could be the salary of the same person, something like that. So basically we can see that P2 and P3 they have that distance between them, whereas P2 and P4 have a greater distance between them, and that means that these 2 points, P2 and P3, they have a certain dissimilarity which is measured by the distance between them. So the distance represents the dissimilarity between the 2 points, and P2 and P4 also have a dissimilarity, and it's greater because you can see that the distance is greater. So let's say if this was age and this was salary, these 2 points, even though they're not identical, they are less dissimilar in terms of age and salary than P2 and P4. And again, these variables are just arbitrary. I'm just calling out arbitrary variables. They could be anything else, and this data set could not be employees, it could be machines, it could be certain observations from nature, and pretty much anything. The point here is that the further away 2 points are, the more dissimilar they are, and that is being measured or captured in our dendrogram by the height of this bar, how high we're setting it. And then the bar itself just shows us that we connected P2 and P3. Alright, so that's our first step in the dendrogram. Next, we're going to move on, and we're going to proceed to the next step in our HT algorithm. We're going to perform step 3. So we're going to find the next 2 closest clusters and connect them. So here we've got each point out of these 4 is a cluster, and then we've got this cluster. Now we need to find the 2 closest out of all of them. And let's say, or from what we see, these 2 are the closest. So let's outline them. There we are. And so now they form their own cluster. Now we want to point that out in the dendrogram as well. So again, we're going to place this horizontal line. Again, how high do we place it? Do we place it higher or lower than this line? Well, we agreed that this vertical axis represents the Euclidean distance, and Euclidean distance represents the dissimilarity between 2 of our observations. So here we can see that P5 and P6, they're actually further apart than P2 and P3, and that is of course natural, because if P5 and P6 were closer, then in the previous step we wouldn't have put P2 and P3 in one cluster. We would have put P5 and P6 in one cluster. Remember, we're always looking for the closest, and then we're moving on to the next step. So P2 and P3 were the closest, and that's why this distance is such. P5 and P6 are further apart from each other than P2 and P3, so the distance has to be greater. And that's why we're gonna show that on the dendrogram. You can see that this bar is set higher. All right. And the next step is to, again, repeat step 3. So we're going to look among all of these clusters, which are the closest. So there we go. So this one was the closest. So I'm going to go back here. This cluster is closer to this cluster than to any other cluster. And pretty much out of all the distances between the clusters, this is the lowest. Again, a lot here is determined by how you measure distances. We can see that the distance between P4 and this cluster is quite close to this distance, but we're going to say that this distance is the lowest. All right, so what we do next is we combine these clusters into one cluster. Let's do that. There it is. So now we have one cluster. Now we need to represent that somehow here. So what we just did is we took this cluster that we have, P2 and P3, connected it with P1. So again, we're going to draw a line, and we're going to draw our vertical lines here again. And once again, the distance here from P1 to the top over here represents the dissimilarity between that cluster that we had and the point that we connected it to. All right, so now let's connect. Let's find what's the next step. Next step again is step 3, and we're going to look out of 1, 2, 3 clusters that we have, which are the closest. Well, obviously it's P4, and it's the closest to these. Again, there it is. We're expanding that cluster. Now we're going to represent on the dendrogram. As you can see, the line is about the same height as this previous line, because the distance between P1 and this cluster was about the same as the distance between P4 and P5 and P6. Maybe this one was a bit greater. Sometimes it's hard to tell, and that's why we have algorithms. That's why machines do it for us. One of the reasons. that's what our dendrogram looks so far. And our final step is to combine these two remaining clusters, because by default they are going to be the closest since there are no other clusters. So we're going to combine them and represent that on our dendrogram. So here the line is very high because the distance or the dissimilarity was very high between these two clusters. And there we go. So that is how we construct our dendrogram. Slowly from the bottom up, it's being constructed, and at the end we've got that one cluster. So all of this is one cluster. And that is what I mean when I say that the dendrogram contains the memory of the hierarchical clustering algorithm. So you can, just by looking at the dendrogram, understand in which order these clusters were formed. And here I've got an example. So this is the actual example generated by computer, generated by an algorithm, showing us the hierarchical clustering. So we've got the points here and we've got the dendrogram over here. So this is what it actually looks like. All right, so now we know how dendrograms are constructed. In the next tutorial, we will learn how to use them to enhance our, or actually execute our hierarchical clustering algorithm. So there we go. Hope you enjoyed today's tutorial. I look forward to seeing you next time. And until then, enjoy machine learning. Hello and welcome back to the course on machine learning. We've already talked about hierarchical clustering and how the algorithm works. Also, we talked about dendrograms and how they are constructed. Today, we're going to put the two together and learn how to get the maximum value out of our hierarchical clustering algorithms. So let's get straight into it. All right, so here we've got an example. The example that we looked at previously, where on the left we've got the points in our scatter plot, and then here on the right we've got the dendrogram, which contains memory of how the clusters were formed during the hierarchical clustering algorithm. So here we can tell right away from, first of all, P2 and P3 were combined into a cluster. Then because their height is the lowest, the height of this bar is the lowest, then we look at the next lowest bar is this one. So P5 and P6 are the least dissimilar out of the remaining. And then these are pretty much the same height, but we first performed clustering. We combined these into one cluster. So P1 was added to cluster P2, P3, then P4 was added to cluster P5, P6, and then at the end, all of the points were combined into one cluster. So that's what the dendrogram is telling us. As you can see right away, it's giving us a lot of additional information on top of the scatter plot, and it contains that memory of the hierarchical clustering algorithm. So how do we use this dendrogram to understand how to best execute or get the most value out of the HC? So let's have a look. What we need to do with the dendrogram, or what we can do, is look at horizontal levels and set thresholds. So we can set height thresholds, or distance thresholds, or also called dissimilarity thresholds, because this vertical axis measures the Euclidean distance between points, which also represents the dissimilarity between them, or points or clusters. So what we can do is set a threshold for our dissimilarity, and we can say that we don't want dissimilarity to be greater than this level. So again, it doesn't matter what the absolute value is, it matters what the relative value is and how it looks on this image. So we're setting the dissimilarity threshold, and we're saying that anything, if we come across clusters that are above this threshold, so we don't want within a cluster to have dissimilarity above this threshold. So what that'll do is it'll give us two clusters. Let's have a look at them. There's our first cluster and there's our second cluster, and that makes sense. So what that is telling us is that within each one of these clusters, the dissimilarity is always less than our threshold. So let's say we've got some values here. Let's say this is 1.5, this is 2.0. So let's say we want to set the threshold at 1.7, and what this is doing is it is not allowing any clusters that would have dissimilarity of greater than 1.7 within them. And as you can see from the dendrogram, we can tell that everything below that level, this cluster and this cluster, they don't have dissimilarity of 1.7 because dissimilarity is represented by these vertical lines. And that's how the concept of thresholding works. And the interesting part about dendrograms is you can quickly tell how many clusters you will have at a certain threshold by just looking at how many vertical lines this horizontal threshold actually crosses. So here you can see it crosses 2 vertical lines. That means we will have 2 clusters. It will be this cluster with all these points, P1, P2, P3, and this cluster P4, P5, P6. All right, so let's have a look at another example. Let's have a look at an example where we put the threshold at this level. So somewhere just below where we combined, as you remember, we had P5, P6 in one cluster, P2, P3 in one cluster, P4 by itself, P1 by itself, and then we combine P1 with this cluster, P4 with this cluster. So let's say we're setting the threshold at just before that level of dissimilarity, which allowed us to combine P1 with this cluster and P4 with this cluster. So what that will do is it will give us a certain number of clusters. So can you tell just by looking at the dendrogram how many clusters we'll have? Exactly correct. We're going to have 4 clusters because it crosses 4 vertical lines. 1, 2, 3, 4, right? So we're going to have a cluster P1, cluster with P2 and P3, cluster with P4, cluster with P5 and P6. Let's have a look. 4 clusters, and there they are. So that is what we're going to get if we set the dissimilarity or distance threshold at that level. Let's try another one. Let's say we want to set our dissimilarity threshold very low at 0.3, meaning that we don't want clusters that have any points within them that have dissimilarity greater than this threshold. So we're not going to allow any clusters like that. And the interesting part here is that we're actually setting the threshold below our very first cluster that we created over here, P2 and P3. So we're not even going to allow P2 and P3 to be combined in one cluster. We're going to say that dissimilarity level, that distance between them, is too great, too high. We don't think that, based on our business knowledge or based on our other internal research or external research, that we don't think that any points with dissimilarity greater than this level should be combined into a cluster. It just doesn't make sense from a business perspective, from a perspective of knowledge about what this data set is about. And what that will do is it will create 6 clusters because we cross 6 lines, 1, 2, 3, 4, 5, 6, and there they are. Every single point will be in its own cluster. As you can see, we've got 6 clusters. So that is how a dendrogram works, or how you can get value out of a dendrogram, and you can set this threshold at different levels to understand how many clusters you'll get. Just by looking at the dendrogram, you can tell right away, and you can that way find the optimal level for the threshold, or the optimal number of clusters that suits your project the best. So, but how do you find the actual, not just an optimal number of clusters that you think is optimal? What is the dendrogram giving us any ideas about the optimal number of clusters? What can we tell from the dendrogram that might be a good guide for us to select the optimal number of clusters? Well, there's a great giveaway that the dendrogram contains, and that is the vertical distance, because it is measuring a dissimilarity. So one of the standard approaches is just to look for the highest vertical distance that you can find on the dendrogram. So basically any line that will not cross any horizontal lines. So for instance, this line can be considered. This line can be considered. This line cannot be considered for that research because it crosses hypothetical horizontal lines. So what you need to do is kind of like every horizontal line you have, just imagine it extends all the way across the dendrogram. Every single horizontal line you have. And now find the longest line among your existing vertical lines that doesn't cross any of these extended horizontal lines. So for instance, even this line cannot be considered for that purpose because it would hypothetically cross this horizontal line that we have coming from this red line between P5 and P6. Again, this line cannot be considered because it's crossing this line. So you would need to look at this line, for example, or this line, or if you wanted to use this line, you would need to use only a bit of it, that part or this part. So you can only use parts of lines that are between horizontal lines. So out of all of the lines that you have here, which is the longest that doesn't cross any extended horizontal lines? Well, that's correct. This one over here is the longest one, or basically in our example, the green and the red, they were about the same height. So this one or this one are the longest ones. And so this is the largest distance, and therefore the best or the recommended approach, again, it's not a set in stone approach. It's kind of one of the things that you could do is take a threshold that will cross this largest distance. So cross that largest distance with a threshold, and then use that threshold to calculate the optimal number of clusters and actually find them. So once we've crossed this largest distance with our threshold, it doesn't matter where you set it. You can set it here, you can set it lower, you can set it higher, as long as it crosses this line. then now the two clusters are this one and this one. As you can see, that is considered to be one of the approaches, or this approach is telling us that the optimal number of clusters is 2, and these are them. And kind of in this case, it makes sense. You can see that indeed these points look as if they're closer together, and these points look as if they're closer together rather than getting any clusters in between them, or even breaking up into more clusters wouldn't make as much sense as this makes sense. And so there you go. That's one of the approaches that you can use. You can still look at this whole problem using similar approach to k-means, where you use the elbow method, so you could use something like that. But in hierarchical clustering, we're going to focus on this approach with the largest distance. And now let's quickly have a knowledge test. So I have two charts here which are hidden. On the left we've got the scatter plot, on the right we've got the dendrogram. I'm going to show you only the dendrogram, and I'd like you to try to understand or try to assess very quickly what's going on the scatter plot. So for instance, we'd like to know, even without seeing the scatter plot or the data set at the moment, we'd like to know what is the optimal number of clusters in this data set just by looking at the dendrogram. Can you identify that? So if you like, you can pause the video and just look at these vertical and horizontal lines and try to find out, based on the method that we discussed, what would be the optimal number of clusters. So in 3, 2, 1, I'm going to now reveal how I would solve this challenge. Well, what I would do is I'd look for the longest vertical line that doesn't cross any extended horizontal lines. So if you extend that, extend that, extend that, you can see that it's probably this line over here. And so that's the largest distance. That means we need to cross it with a horizontal line with our threshold, and that will give us the number of clusters, which is 3 clusters, because it crosses 3 lines here. 1, 2, 3. And if we look at the chart, as you can see, indeed we do have 3 clusters, and it does look like that is the optimal number of clusters for this business problem. So hopefully you enjoyed this tutorial. We walked through all of this manually so that you have a better intuitive understanding of how the hierarchical clustering algorithm and dendrograms work. And next, Hadlong will show you around in R and Python, and together you will create some amazing analysis around hierarchical clustering. And together with him, you will solve a business problem using the hierarchical clustering algorithm. You've got some fun tutorials ahead of you, and I look forward to seeing you next time. Until then, enjoy machine learning. Hello and welcome back to the course on machine learning. This is a quick tutorial to update you on how to download the dataset for this section. If you've seen this tutorial before, then feel free to skip it. However, if you're jumping into this course, into this section directly, just because you perhaps needed to learn this specific machine learning algorithm, then make sure to go back and first complete the data pre-processing section, because you will need that throughout this section as well. And you'll also need the machine learning template folder, which we're going to use just now. So in order to get the dataset for this section, you need to go to www.superdatascience.com/machine learning. Machine learning is spelled with a hyphen in between, 2 words with a hyphen. And then you'll see this whole page dedicated specifically to this course, and all the datasets for this course are available on this page. And so let's say that today you want to do the k nearest neighbor algorithm section. Of course, it is most likely a different section. I'm just going to use this one as an example, but just go ahead and find your section on this page and then perform the same exact steps, and you will see how to download and install the dataset. So I'm going to do it for the k nearest neighbors algorithm section. So just go ahead and click and download that dataset. It should download pretty quickly, unless it's one of those larger datasets that we also have in this course. Then you have the dataset here, and we already have the machine learning A to Z folder, which we created or downloaded from the data pre-processing section. So now we're going to take this, we're going to open the folder. We're going to go to into the part which this algorithm relates to. Then we'll find the algorithm, there it is, k nearest neighbors, and then we'll take this folder, this dataset folder, and we'll drag it in here. Now we're going to unarchive this folder. So I'm going to say right click extract here, If you get this Mac OS folder, sometimes it appears, then you don't really need it. Everything is in the normal folder, so you can get rid of the Mac OS folder and you can get rid of the zip folder now. And also with the k-nearest neighbors, you just need to take all of the files and copy them into this folder here. So we don't need this another level of hierarchy, so you can now delete it. So basically what you should be left with is machine learning A to Z, then the part that the algorithm is in, then the section that you are interested in, and then this is where all the files should be stored. So here you'll have some Python and R templates, and you'll also have the dataset. That's the one that you will need in this section of the course. So there we go. It's a very straightforward process, and the beauty of it is if you use our machine learning A to Z template folder, which we provide at the start of the course, you will end up with a very structured set of folders which contain your datasets, and you will build them up as you go through the course, and therefore you'll have the whole library and it will be nicely and neatly organized. I hope you enjoyed today's session and have fun on the practical tutorials, and I'll see you here next time. Until then, enjoy machine learning.
Hello and welcome to this Python tutorials. So in the following tutorials we're going to solve our business problem, but this time it's going to be with hierarchical clustering, which you will see is exactly the same as k-means clustering. Okay, so let's start by setting our working directory. So we click on this folder here to choose the working directory. Then we go to Machine Learning AZ, Part 3 Clustering, Hierarchical Clustering, and we click on Choose. Okay, and then we don't forget to click on this little button here to set the chosen folder as working directory. And then we can go to File Explorer to make sure that we are in the right folder and that our dataset is well imported. So let's select the code here to import the libraries and execute. And now let's start with the first step, which is to import the mall dataset with pandas. So as usual, we are going to introduce a new code section here with the comment importing the mall dataset with pandas. And then let's immediately import the mall dataset. So we create this new variable here, dataset, and then we write equals pd dot read underscore csv, and then in parentheses we put the name of our dataset mall.csv in quotes. Okay, now let's select and execute this line of code. Done. And now let's go to Variable Explorer to find our dataset. Okay, so here it is. Let's double click on it, and then let's give a quick reminder of what this dataset is about. So there is this big mall in a small city where most people go to, and people can buy anything in this mall, whether it is food, clothes, smartphones, computers, beds, whatever they need. And the mall gathered some information of 200 of their customers, which are customers that not only subscribe to the membership card, but customers who are also coming very often to the mall, so that it's, insightful information of their customers. Then the mall assigned a customer ID to each of these customers, and then from the membership form that customers filled in when they subscribed to the membership card, the mall took their gender, their age, and their annual income. And then based on several criteria, like the income, the number of times the customer shows up in the mall, and of course the amount of money they spend in the mall computed a spending score for each of their customers. This spending score takes values between 1 and 100, and what it simply means is that the closer the spending score is to 1, the less the customer spends, and the closer the spending score is to 100, the more the customer spends. So why did the mall do that? It's because the mall would like to segment their customers into different groups, but the problem is that the mall has actually no idea of what these groups might be. It doesn't even have any idea of how many groups they're looking for. And that's specifically what makes this business problem a clustering problem. Because we don't know what the answers are. We don't know the final categories ahead of time. So that's our mission, to find some unknown clusters of customers. We solved this problem with k-means, and now let's do this with hierarchical clustering. Okay, so we are good with the dataset, it's well imported. And now what we have to do left is to select our columns of interest, which are of course the columns annual income and the spending score. So we are going to put these two columns on a variable x. So we write here x equals dataset.iloc, and then in square brackets colon to take all the lines of our data set, then comma, and then now we're going to pick the 2 columns that we're interested in. So let's see what the indexes are. Let's go back to our data set. We know that indexes in Python start at 0, so let's count 0, 1, 2, and then annual income has index 3, and spending score has index 4. So let's go back to our code, and now let's write 3, comma, 4 in square brackets, and that selects our columns, annual income and spending score. And then we just add at the end, dot, values. Okay, so let's select this line and execute. Perfect. Our array X just appeared in Variable Explorer, so let's double click on it to make sure everything is fine. Perfect, we have our 2 columns, annual income and spending score, and we have our 200 of observations. Great, so that's the end of step 1. We imported our data set and prepared the data correctly. So that's it for this tutorial, and in the next tutorial we're going to move on to the next step, which is to use the dendrogram to find the optimal number of clusters. So I look forward to seeing you there, and until then, have a good one. Hello and welcome to this Python tutorial. So in the previous tutorial we imported the mall dataset with pandas, and we prepared the X variable, which contains our 2 columns of interest, the column annual income and the column spending score. So as you can notice, so far we did exactly the same thing as in k-means. And you're going to see that in this new step that we are about to do right now, we are going to do the same action plan. Because remember, when we used k-means in the previous section, at this stage we used the elbow method to find the optimal number of clusters. And here in hierarchical clustering, this new step also consists of finding the optimal number of clusters, only this time we're not going to use the elbow method, we are going to use the dendrogram. So let's do this. Let's plot our dendrogram for this business problem, and then we're going to have a look at our dendrogram, and we're going to use the method that Kirill explained in the intuition section to find this optimal number of clusters. So here we go. Let's introduce a new section here with the comment using the dendrogram to find the optimal number of clusters, and let's immediately write the code to plot this dendrogram. Okay, so the first thing we're going to do is to import SciPy. SciPy is an open source Python library that contains tools to do hierarchical clustering and build dendrograms. So to import SciPy, we're not going to import the whole SciPy library, we're going to import the tools that we are interested in to build our dendrogram. So we type import SciPy dot cluster dot hierarchy, so that's all the part of SciPy library to do hierarchical clustering. And to simplify this huge name, we're going to call it SCH. That will be more simple when we use it afterwards. Okay, so now we have everything we need to build the dendrogram. And now the awesome thing is that we are going to be able to build our dendrogram with only 1 line of code. So let's immediately write the single line of code. We start by creating the variable dendrogram equals, then SCH, which is the shortcut for SciPy cluster hierarchy, dot, and then dendrogram, which is actually the routine that makes all the process that Kirill explained in the intuition section. And in parenthesis, we add SCH dot linkage. So linkage is actually the algorithm itself of hierarchical clustering. And then in linkage, we have to specify on which data we apply the linkage. So that's X, that's our first parameter, then comma, and then as a second parameter, we add the method. That is the method that is used to find the clusters. And we are going to choose the ward method. So here we write method equals ward in quote. So what is this ward method? It's actually a method that tries to minimize the variance within each cluster. Remember in k-means when we were trying to minimize the within cluster sum of squares to plot our elbow method chart? Well, here it's almost the same. The only difference is that instead of minimizing the within cluster sum of squares, we are minimizing the within cluster variance. That is the variance within each cluster. And that's it. With this single line of code, we managed to build our dendrogram. It's not like in the elbow method when we had to make a for loop. Here, with only 1 line of code, we managed to build our dendrogram. And so now we're going to give it a title, a name on the x-axis and a name on the y-axis. And let's see what happens. So we add here plt.title, and let's choose the title dendrogram, plt.xlabel, and in parentheses customers, because on the x-axis are going to be all our customers, and then let's give a label to our y-axis by typing plt.ylabel, and we're going to put Euclidean distances, because actually the vertical lines in the dendrogram are the distances between the clusters, that is between the centroids of the clusters. And then of course we add plt.show parenthesis to specify that our plot is done and ready to be displayed. Okay, so now let's cross our fingers and hope that it's gonna work, that is that we're gonna find the same result as we found in k-means, which, if you followed the k-means section, was an optimal number of 5 clusters that we had found with the elbow method. So let's select this whole code section, Command or Control plus Enter to execute. And here is our beautiful dendrogram. Okay, so let's describe this tree. At the bottom we have all our customers, and the vertical lines that we see on this dendrogram are the distances, the Euclidean distances between the clusters. And this dendrogram represents all the different clusters that were found during all the hierarchical clustering process that Kirill explained in the intuition section. And right now what we want to do is to find the optimal number of clusters. So how do we do that? We look for the largest distance that we can make vertically without crossing any horizontal line. And we can clearly see that this largest distance is right here. That is, I start from here, and then I go down, and by going down I make sure I don't cross any horizontal line. Okay, go down, no horizontal line, go down, and then suddenly I cross this horizontal line. So finally, from here to here is the largest distance I can make without crossing any horizontal line. And now to find the optimal number of clusters, we just need to count the number of vertical lines in this space here, and that is 1, 2, 3, 4, and 5. Perfect, so that's exactly the same result as we obtained with k-means with the elbow method, so we're very happy and we can move on to the next step. And remember, at this stage with the k-means algorithm, the next step was to fit the k-means algorithm to our data x. And here it's the same again, since we just found the optimal number of clusters, our next step will be to fit the hierarchical clustering algorithm to our data x. And this is what we're going to do in the next tutorial. So I look forward to seeing you there, and until then, happy learning! Hello and welcome to this Python tutorial. So in the previous tutorial we plotted our dendrogram and we used it to find the optimal number of clusters, which was 5 clusters. And now, since we have the right number of clusters, we are ready to move on to the next step, which is to fit our hierarchical clustering algorithm to our data with the right number of clusters, 5 clusters. So again, this third step of hierarchical clustering is the exact same third step as in k-means clustering. Okay, so now let's introduce a new section with the comment fitting hierarchical clustering to the mall dataset. Okay, so the first thing that we have to do is to import the right tool that is going to help us to fit the hierarchical clustering algorithm to our data X. Remember that in k-means this tool was the k-means class, and here it's going to be the same. We are going to use a hierarchical clustering class to fit hierarchical clustering to our data in a flashlight. Okay, so what is this class going to be? Remember in the intuition section, Kirill talked about 2 algorithms for hierarchical clustering. One is agglomerative hierarchical clustering, and the other one is divisive hierarchical clustering. He also said that the most common one was agglomerative clustering, so the class that we're going to import right now to fit hierarchical clustering to our mall dataset is going to be the agglomerative clustering class from the awesome scikit-learn. Therefore, let's import this class. So we write from sklearn.cluster import agglomerative clustering. Remember the k-means class was with a capital K and capital M. Well, here it's the same, it's capital A and capital C. Okay, and now we are ready to fit the hierarchical clustering, that is the agglomerative hierarchical clustering, to our data X. And same as k-means, we start by creating an object of the class agglomerative clustering. So we type hc equals agglomerative clustering. And now in the subject, in parentheses, we are going to specify the different parameters. So the first parameter is n clusters, the number of clusters, which now we know is 5. So we type n clusters equals 5. Then the second parameter is affinity, which is actually the distance to, do the linkage. And as usual, we're going to choose the Euclidean distance. So we add the second parameter, affinity equals Euclidean. And finally, the last parameter and the most important one is the linkage. So we're going to use the same linkage as the one we used when we built our dendrogram, which, as you remember, is the Ward linkage, the Ward method, which I remind is a method that is trying to minimize the variance in each of the clusters. Okay, so by writing this line, we just prepared the hierarchical clustering algorithm, because as you notice, we haven't input our data X yet. So we haven't fit the hierarchical clustering algorithm to our data X. However, we are going to do just that right now. So let's write a new line of code. And in this line of code, we're going to fit the hierarchical clustering algorithm to our data X while creating the clusters vector. That is the vector that tells for each customer which cluster the customer belongs to. So we're going to call this vector y_hc, then equals. Then we take our object hc that contains the agglomerative clustering algorithm ready with the correct numbers of clusters, 5 clusters, the Euclidean distance, and the word linkage. And now, same as k-means class that contains the fitPredict method, the agglomerative clustering class also contains the fitPredict method, and so we add here dot fit_predict, that is the fitPredict method that is going to return the vector of clusters, and then in parentheses x, to of course specify that we are fitting the agglomerative clustering algorithm to our data X, and that we're predicting the clusters of customers of our data X. So basically we just did exactly the same as in k-means. The only difference is the class that we use, which is here agglomerative clustering instead of k-means. Great, so we are done with the fitting section. So let's select this code section here and execute it. Alright, and now we can see that in Variable Explorer, this new vector of clusters yhc appeared. So let's double click on it. And let's also open the dataset to see the associations. So the first customer ID number 1, belongs to cluster 4. Then customer ID number 44 belongs to cluster 1. And our last customer, the customer ID number 200, belongs to cluster 2. Alright, so we are done with this new step of fitting the hierarchical clustering algorithm to our data X. So that means that we did a great job, we can actually be proud of all our achievements. And so now we deserve to have a little fun, which is exactly what we are going to get in the next step. So I look forward to seeing you in the next tutorial, and until then, happy clustering. Hello and welcome to this Python tutorial. So in the previous tutorials, we did our first 3 steps in our hierarchical clustering journey. First step was to import our dataset and prepare our data X that contains the 2 columns we are interested in, the annual income and the spending score. Then second step, we used the dendrogram to find the optimal number of clusters, and by doing that we found 5 clusters. And then in the third step, we fitted our hierarchical clustering algorithm to our dataset by using the agglomerative clustering class with the parameters number of clusters equals 5, a Euclidean distance, and a word linkage. And then we fitted this prepared agglomerative clustering algorithm to our data X by using the fitPredict method that not only fits the agglomerative clustering to our data X, but also creates the vector of clusters that returns for each customer which cluster the customer belongs to. Okay, so by doing those 3 steps, we did our job. We fitted correctly the hierarchical clustering algorithm to our data X. And now, time for a little fun. Let's visualize all our results and especially the clusters of customers. You know, it's like a movie director who just finished making his movie, and after he did his great job, he's going to watch the premiere. Well, it's the same for us here. We did a great job fitting the hierarchical clustering to our dataset, and now we're going to watch the premiere of hierarchical clustering results. Okay, so let's introduce a new section here, visualizing the clusters. And actually the code that we're going to put here in this new step is the exact same code as we used in the k-means step for visualizing the clusters. So let's be efficient, let's not retype the whole code for this section, and let's go to File Explorer to take our k-means Python code. So we need to click on this up arrow here to go to the previous folder. Then we open our k-means section folder here, and then we double click on this Python file here, which is the Python code that we used when we implemented k-means on Python. And here let's just copy the last section visualizing the clusters, and let's go back to our Python file for hierarchical clustering, and let's paste it here. And you're gonna see immediately that we only have to replace one tiny little thing. Can you guess what it is? Okay, so let's go back to our k-means Python file. As you can see in the step fitting k-means to the mall dataset, here we use the k-means class to prepare our k-means algorithm, and then we use the fit_predict method to fit the k-means algorithm to our data X and create the vector of clusters y k-means. And then in the last step, visualizing the clusters, you can see that we use this vector of cluster y k-means here in each of the plot scatter that plots the different clusters. So let's go back to our hierarchical clustering Python file. And as you can see in the fitting hierarchical clustering to the mall dataset step, it's exactly the same as in k-means. The only difference is that we call our vector of clusters yhc instead of y k-means. So in this last step visualizing the clusters here, the only thing that we have to do is replace y k-means by yhc. And that's because we took exactly the same approach with the exact same code structure in both k-means and hierarchical clustering. Okay, so let's do this. Let's replace y k-means by yhc. Okay, so I'm gonna do it quickly. We press Command and Control plus R, and here we replace y k-means by yhc. And what we also need to do is to remove this line that was used to plot the cluster centroids in the k-means algorithm. So here we won't need it for hierarchical clustering, so let's get rid of it. Alright, and now all we have to do left is select this code section here and press Command and Control plus Enter to execute it and start watching the premiere. So that's the end of this tutorial. I will let you enjoy the premiere, and in the next tutorial we will be doing our analysis of the clustering results, and I will explain how you can reuse this code for your business problem. So now I'm gonna press Command plus Enter to execute, and enjoy the show. Hello and welcome to this tutorial. So I hope you enjoyed watching the premiere of the hierarchical clustering results, and that you took the time to analyze them, to either compare them to the k-means results if you followed the k-means section, or if you did not do the k-means section before, then it's great if you took the time to understand what those clusters are. Okay, so now let's look at the clusters one by one. So the cluster 1 is this red cluster here, and customers in this cluster have high income and low spending score. But remember, all the customers in the dataset are customers that subscribe to the membership card and are also customers who come often to the mall. So that means that these customers, although they have high income and come often to the mall, they don't spend much money in the mall. So in the k-means section we call these customers careful customers, because they're careful with the money they're spending even if they earn a lot. Okay, so now the second cluster is the cluster in the middle, the blue cluster, and the customers in this cluster have average income and average spending score. So we call this cluster standard customers. Then cluster 3 is the green cluster here, and it contains customers that have high income and high spending score. So that's a very interesting cluster for the mall, because customers in this cluster have a lot of money and they like spending their money in the mall. So typically this would be the cluster of customers target of the marketing campaigns, because it's the most interesting cluster of customers for the mall. However, of course, we would need to check the volumes of the two clusters, target and standard, because maybe there are a lot more customers in the standard cluster, which then would imply that the main revenue stream comes from this cluster of customers, the standard cluster. So we would need to check that, but so far these are the first insights that we can give. And it would be very interesting for the mall to see what kind of products are bought by the customers in this cluster, to maybe allocate more budget on these marketing campaigns for these products. Okay, and now cluster 4. Cluster 4 is the cyan cluster on the up left corner. So this cluster contains the customers that have low income but high spending score. And so these customers are maybe not very careful with the money they spend, and so we call them the careless customers. You know, it can be, for example, young people who just had their first salary and they're so excited about that, so they cannot resist to spend their whole monthly salary in the mall. And finally, the final cluster, cluster 5. So here customers in this cluster have a low income and a low spending score. So this time these customers are more sensible because they manage their money as they should. So we call these cluster of customers sensible. And so now you could totally show this plot in a presentation and give the insights that we just talked about. Okay, so we're very close to the end of the Python tutorials for hierarchical clustering. The only thing that I want to show you now is how you can reuse this code for your business problem. So that's very simple. You just have to change the name of your dataset here, and then you change the indexes of your columns of interest, because maybe you will need more columns of interest. And then you're good to go. You just have to select this code and execute it, and you will have your results. But be careful. If you are doing clustering in more than 2 dimensions, then don't execute the last code section here because it's only for plotting the clusters in 2 dimensions. However, later in this course we will see a super powerful technique that will allow us to reduce the dimensions of our dataset. So for example, if we are doing a clustering analysis with more than 2 dimensions, we will be able to reduce the number of dimensions to 2 dimensions, and in that case you can select this last code section here, visualizing the clusters, to see your clusters in 2 dimensions. Okay, so that's the end of this section on hierarchical clustering with Python. Thank you for watching these tutorials, and I look forward to seeing you either in the following R tutorials if you're interested in R, or in the next section of this course. Until then, happy learning! Hello and welcome to this R tutorials. So, in the previous tutorials we solved our business problem in Python using hierarchical clustering, and this time we're going to solve it in R, and you're going to see that it's exactly the same. We are going to import our mall dataset first, then we're going to use the dendrogram to find the optimal number of clusters, then we will fit hierarchical clustering to our mall dataset, and then finally we will visualize our results. So in this tutorial we're going to do the first step, which is to import the mall dataset, so let's start doing it right now. But before that, let's not forget to set our working directory. So here I'm on my desktop, this is my machine learning AZ folder, let's open it. Then let's go to part 3, clustering, then hierarchical clustering, and now we click on this more button here, we click on set as working directory, and that sets our hierarchical clustering folder as working directory. So let's make sure we have our mall dataset in the folder. Here it is, perfect, we are ready to start. Okay, so let's introduce a new section with the comment importing the mall dataset. Here we go, and now let's import our dataset. So we create this new variable dataset equals read.csv, and in parentheses we put the name of our dataset mall.csv in quotes. Okay, so let's select this line and execute. And now our dataset appears in data, so let's click on it, and here it is. So for those of you who didn't follow the Python tutorials, I'll just give a quick reminder of what this dataset is about. So basically these are informations of customers in a mall, which are customers that not only subscribe to the membership card, but also come often to the mall. And the mall gathered some information of 200 of these customers, their gender, their age, their annual income. And then for each of these customers, they computed a spending score. So this spending score takes values between 1 and 100. And the closer the spending score is to 1, the less the customer spends. And the closer the spending score is to 100, the more the customer spends. Okay, so we have these informations, and now our mission is to find some groups of customers, but since we have no idea of what kind of groups we're looking for, or even the number of groups of customers we're looking for, this specifically makes this business problem a clustering problem, because we don't know the answers, we don't know the final results, and more precisely, we don't know the final categories of our customers. Okay, so we imported our dataset, and now what we have to do is to prepare our data, because we want to do this clustering only based on the annual income and the spending score. So let's create a new variable x equals dataset, and then in square brackets we're going to put the 2 indexes of our columns of interest, which are, let's go back to our dataset. Indexes in R start at 1, so customer ID as index 1, gender as index 2, age as index 3, annual income as index 4, and spending score as index 5. Okay, so here in the square brackets we add for column 5. That takes our column annual income and spending score. And now let's select this line of code and execute it. And here it is, our X variable appears in the data. Let's click on it to make sure everything is fine. Okay, perfect, we have our 2 columns annual income and spending score and our 200 observations. Perfect, so we completed our first step. So that's the end of this tutorial. And in the next tutorial things are going to get more interesting. We're going to use the dendrogram to find the optimal number of clusters. And you're going to see what a dendrogram looks like in R. Thank you for watching this video and I look forward to seeing you in the next tutorial. Hello and welcome to this R tutorial. In the previous tutorial we imported our mall dataset and we prepared our data correctly by taking the 2 columns we're interested in, the annual income and the spending score. So we created this variable X that contains these 2 columns. And now things are going to get much more interesting because in this tutorial we are going to build our dendrogram and we will use it to find the optimal number of clusters, exactly like we did in the k-means section, where, as you remember, in step 2 we used the elbow method chart to find the optimal number of clusters. Well, here in hierarchical clustering step 2, we will also look for this optimal number of clusters, only this time we're not going to use the elbow method, we're going to use the dendrogram. So let's do that right now. The very cool thing about it is that we only need 1 line of code to build this dendrogram. So let's write this line of code. We start by creating our variable dendrogram, then equals, and then we're going to use the class hclust. So let's type hclust here, and then let's press F1, and here we have all the info of this hclust class. So let's look at the arguments. Here we only need the first 2 arguments. The first argument is a dissimilarity structure as produced by dist. And in our case, this parameter is going to be the distance matrix of our dataset X, which is a matrix that tells for each pair of customers the Euclidean distance between the 2. So that means that for each pair of customers, we take the 2 coordinates annual income and spending score, and we compute the Euclidean distance between the 2 based on these coordinates. Okay, so that was just to explain the first parameter of the hclust class. And so let's input it in our code. We input dist, and in parentheses x, comma, and then method equals Euclidean. So that specifies that we want to compute the Euclidean distance matrix for our data x. Okay, so that's the first parameter, this distance matrix, and now the second parameter is the method. So this method is simply the method used to find the clusters. And like in Python, we're going to choose the most common method, which is the ward method. Here it's called ward.d, and it's actually a method that is trying to minimize the variance within each cluster, kind of like what we did in k-means when we were trying to minimize the within cluster sum of squares. Well, here it's based on the same idea, but instead of trying to minimize the within cluster sum of squares, we're trying to minimize the within cluster variance to find our clusters. So here we write method equals ward.d. So that is the end of the line to build this dendrogram, and now we just need to plot it. So just below we're going to write plot, then in parentheses dendrogram. Then let's give it a title by typing main equals paste parentheses dendrogram in quotes. Then let's give a name to the x-axis by adding xlab equals customers, because in the dendrogram all our customers are going to be on the x-axis. And then finally let's give a name to our y label. We're going to call it Euclidean distances, and that's because in the dendrogram the vertical lines that we're going to see are actually the Euclidean distances of the clusters, that is between the centroids of the clusters. Okay, so we are good to go with our plot, and our dendrogram actually. So let's select all this code section here, execute, and here is our dendrogram. So let's have a look at it. I'm clicking on zoom here to make it bigger. Okay. And now let's try to find the optimal number of clusters thanks to this dendrogram. So as Kirill explained in the intuition section, to find this optimal number of clusters, we need to find the largest vertical distance that we can make without crossing any other horizontal line. And then we just need to count the number of vertical lines at this level. Okay, so let's start by finding the largest vertical distance. So it's not here, obviously. then maybe this one, it's quite a large distance. That would actually give us 3 clusters, because as you can see here, I'm crossing 3 vertical lines. Definitely not this one. And here we have another large distance. You see, from this point to this point is quite a large distance. And then below, obviously, we don't have any large distance. So now the question is, what is the largest distance between this distance and this distance? Well, if you have a better look at it, we can see that the largest distance is actually this distance. And how many vertical lines do we have at this level? Let's see, 1, 2, 3, 4, and 5. So that means that our optimal number of clusters is 5 clusters. And that's of course a relief, because that's what we obtained with the k-means algorithm using the elbow method. So everything is fine, everything is perfectly coherent. So we well completed our second step, and now we're ready to move on to the next step, which is to fit our hierarchical clustering algorithm to our data X. And that's what we will be doing in the next tutorial. Hello and welcome to this R tutorial. So in the previous tutorial, we plotted our dendrogram to find the optimal number of clusters, and the result was 5 clusters. So now in this new step, since we have this optimal number of clusters, we are going to fit the hierarchical clustering algorithm to our data X with obviously 5 clusters. Okay, so the first thing that we need to do is to create an object of the hclust class. And actually, this is something that we already did. Because if we go back to step 2, here when we wrote dendrogram equals hclust, then the distance matrix and the word method, we actually created an object of the hclust class. And we're going to do the exact same thing right now. We're going to create the exact same object from the hclust class. So I'm going to copy this line of code, paste it here in step 3, and I'm just going to change the name of the object just to make things nice and clear. So let's replace here dendrogram by hc, and now we have the same object as before, only with a different name. And this actually makes sense because by building a dendrogram, we actually do all the steps of hierarchical clustering, and among all these steps, there is the step in which the algorithm found 5 clusters. So that means that this object contains the information when we have 5 clusters. And so now let's use this object to build our vector of clusters, that is the vector that will tell us which cluster each customer belongs to. And to build this vector, we're going to use one of the methods of the hclust class, which is the cutTree method. So we're going to call our vector of clusters y_hc equals, then we use the cutTree method of the hclust class. So let's type cutTree and then press F1. And then here we see that this method requires 3 arguments. The first argument is tree, and of course it's our dendrogram that we just renamed hc. Then the second argument is k, the number of clusters. So here we input 5, and we will leave the default value for the third parameter. Okay, and now it's interesting to take a step back, because actually this method is called cutTree, which is a very well chosen name because indeed we are cutting the tree to take the part of the tree that contains our 5 clusters. So that makes pretty much sense. And now, since we are actually done with fitting hierarchical clustering to our MAL dataset, let's select this code section here and execute to find our yhc vector of clusters that appears right here. And now if we type in the console yhc here and press enter, we have all the clusters that the hierarchical clustering algorithm assigned to each customer. So for example, customer number 1 belongs to cluster 1, customer number 2 belongs to cluster 2, customer number 106 belongs to cluster 3, and our last customer belongs to cluster 4. Okay, so congratulations, we found the right number of clusters and we fitted correctly the hierarchical clustering to our MAL dataset. And now, time for fun. In the next tutorial, we will be visualizing our hierarchical clustering results. Hello and welcome to this R tutorial. This tutorial is the fun tutorial because we did our job by finding the optimal number of clusters thanks to the dendrogram and by fitting the hierarchical clustering algorithm to our data X. And now, showtime! We will be visualizing our clusters using the clustplot method. However, we will not rewrite the whole code because, as you will see, we made the exact same code structure as we did for k-means. So now what I'm going to do is I'm going to open our k-means code and I will show you that because we have the same code structure between k-means and hierarchical clustering, we just need to replace one tiny little thing to plot our 5 clusters obtained by hierarchical clustering. So let's go to Files here, then let's click on these 2 dots here to go back to our Part 3 clustering folder to find our k-means clustering folder. And in this k-means folder, let's open the k-means R file. And now let's compare our 2 codes for hierarchical clustering and k-means clustering. So in step 1, we both did exactly the same thing, we imported our mall dataset. Then in step 2, we looked for the optimal number of clusters using 2 different methods, the elbow method for k-means and the dendrogram for hierarchical clustering. Then in step 3, we fitted our algorithm to our data X and we created our vector of clusters, yk-means in k-means and YHC in hierarchical clustering. And now, if we look at the last step, visualizing the clusters in the k-means algorithm, we can see that the only thing in our code that is related to k-means is the yk-means vector here. And we have the same vector of clusters in our hierarchical clustering code, it's YHC, so basically the only thing that we have to do to plot our clusters in hierarchical clustering is to take our clustplot function here with the same parameters, copy it, and paste it in our hierarchical clustering visualizing the clusters, and then the only thing that we have to do is to replace yk-means by YHC. And now it's ready, let's select our code section here, execute it, and voila! That's our hierarchical clustering results. That's the end of this tutorial, but the fun continues in the next tutorial, where we'll be analyzing our results and explain what those clusters are. I will also explain how you can reuse this code for any other business problem, and this will conclude our R tutorials. So I look forward to seeing you in the next tutorial, and until then, enjoy machine learning! And here is our hierarchical clustering results obtained in R. So let's have a closer look at these clusters and understand what they are. Our first cluster is cluster 1, which is the blue cluster right here, and it contains the customers that have high income and high spending score. So that's an interesting cluster for the mall because customers in this cluster have a high income and spend a lot of money in the mall, so this cluster would be a good target of the mall marketing campaigns, and so we can call this cluster the target one. Okay, now cluster 2 contains the customers that have high income and low spending score, and so we can call these customers the careful customers. Now cluster 3, customers in this cluster have average income and average spending score, so we call this cluster the standard cluster. Now cluster 4 has the customers that have low income and low spending score, so that's basically sensible customers who pay attention to the money they spend by paying attention to the money they earn. And eventually cluster 5 contains the customers that have low income but high spending score. So these are customers who are rather careless, especially that 199 customer here who earns a low income but spends a lot of money. So this one should particularly be careful. And actually this cluster 5 here could be a very interesting cluster for the mall company if the latter has a social responsibility, as it is the case for more and more companies today. Alright, so we are done with hierarchical clustering in R. If you want to reuse this code for your business problem, it's very easy. You just have to change the name of the dataset here, then change the indexes of your columns of interest just below. However, if you do clustering in more than 2 dimensions, don't execute the last section visualizing the clusters because it's only for 2 dimensions. But don't delete this section and leave it as comments, because later in this course we will learn a super powerful technique called dimensionality reduction that will reduce the dimensions of your data to perhaps 2 dimensions so that you can use this final section visualizing the clusters to see your clusters in 2 dimensions. Alright, so that's the end of hierarchical clustering in R, and that's also the end of hierarchical clustering, and in the next section we will recap everything we've learned in clustering. Thank you for watching these tutorials. I hope you are now more comfortable with doing clustering in R or Python. I look forward to seeing you in the next tutorials, and until then, happy clustering!